All right. So welcome everyone. Thank you for sparing your time to attend our workshops today. So this is the first workshop on performance engineering, modeling, analysis, and visualization strategy, and we compress it as Permavost. This is the first one of this workshop series. We would like to have interesting discussions with all of you people, because the main idea of the workshop itself is to answer challenge in the modern software engineering, because it gets increasingly complicated, especially in the HPC field. We are dealing with a lot of cutting edge infrastructure and a novel problem, and the scale is unprecedented. So the scale that we are talking right now, it's not only about the supercomputers that getting larger and larger, but also the number of people involved in this community also getting bigger, with the different level of understanding about the scientific software and how to understand what is going on out there. So we put the aspect in here, the analysis and visualization strategy, because most of the stakeholders in this realm of the performance engineering and modeling are not all coming from the computer science background. So this whole idea of the workshop is we want to create a bridge between all of these stakeholders that can communicate and then exchange ideas, so we can have more better design or better concept for the next performance engineering on the analysis for the applications. So that's the general overview about this workshop. About the event today, as you can see in the screen, we have the introduction and also keynote from Dr. Andreas Herten. He's already here. He will share his experience with the Jewels booster for the early user program. So a little bit background about the Jewel booster itself is currently the 7th fastest supercomputer in the world, and also the fastest one in Europe. And we would like to know what are the insights that we can get from this early user experience. And later in the afternoon, we will have lunch break, and we will continue at 1:30 p.m. where we will have papers presentations. We have 3 papers that will be presented here, and in between this paper video, we will give chance to our attendees to ask questions to our presenters. And later, after this paper presentations, we have break and continued with the discussion panel from our 4 experts about the future of performance analysis and engineering. We have Guido Jukland from Helmholtz Centrum in Dresden, Lucas Nor from Federal University of Rio Grande do Sul, Brazil, Max Katz from NVIDIA, also Olga Pierce from Lawrence Livermore. So that's the general overview and introduction of the program today. We are very thankful for you for attending this workshop, and we are also thank our collaborators, which is POP Center of Excellence and also NAG in UK. I think it's time for Dr. Andreas Herten to give the first keynote speech.
All right, thanks, Radita. I would start sharing my screen then, taking over from you.
Yeah, here, I opened it up and I made you a co-presenter, so you should be able to.
Yeah, it works. It works. I think you should now be seeing my slides, right?
Yeah, I can. Let me verify that it's going to be on the.
Perfect.
Yes, and there it is. Okay.
All right, cool. Yeah, good morning or good night, everyone, I guess, depending on your time zone. Thanks, Radita, for the introduction. You've already taken away a few of my first slides, but I won't care. I will just still present them. So my name is Andreas. I'm from Munich Supercomputing Center, and I'm here to present some first early user experiences from our first month with Europe's largest or fastest supercomputer, Joules Booster. I came up with quite a few slides, so I think there should be one slide for everyone, whatever they are interested in. So let's just get started. So just to quickly maybe introduce to you who are not aware of what Jülich Supercomputing Center is, what we are doing. So basically, we're one of the institutes of Forschungszentrum Jülich, which is German for Research Center Jülich, German, one of the largest German research institutes in Germany, located near Cologne in a small town called Jülich, which not a lot of people know. We're doing interdisciplinary research with various institutes, and we do this with over 6,000 people. So quite a large center there. One of the institutes, as said, is Jülich Supercomputing Center, where we are operating different kind of supercomputers. We do education and training with the machines. We provide support for the applications running on there, and also support for the various domains which we have. So we have a quite tight integration with the respected domains which run on our machines. But further, we also do research and development on current and next-gen architectures, both from software and hardware side. Part of that, more or less, covering all those bases, is my lab. That's the Accelerating Devices Lab, where we are doing support, research, and education for accelerating devices, and especially GPUs at the moment. And we have also strong collaboration with NVIDIA within the NVIDIA Application Lab at Jülich already for some years. The most important supercomputers which we have are Joules, Jurica DC, and Yusuf. And there was also a few prototypes where we research and what could be the next generation, or what kind of technology can we use. And those prototypes of relevance are UMax, based on FPGAs, and Deep, which is basically a system which is really looking in how to integrate new technology. Today this talk should be about Joules, and let me just introduce Joules to you. So it's not only Joules Booster, but it's Joules is basically a two-part system. So already in 2018, we installed Joules Cluster in JSC, which is a system based on Intel Skylake CPUs with more than 2,500 nodes. It already then features a few nodes with GPUs equipped. So that was at that time, or is still, the V100 from NVIDIA. And it's only 50 GPUs in there. We just wanted to get our hands dirty in GPUs at that time and figure out how this is really working. For sure, for this kind of an HPC machine, we have also a strong interconnect. In this case, it's Mellanox EDR100 InfiniBand, aligned in a fat tree topology. This system provides 12 petaflop of performance, still going strong, still our more on the multi-purpose side of our scaling supercomputers. And then last year, in November last year, we've inaugurated Joules Booster, which is our new highly scalable system. It only has 936 compute nodes, but those are kind of beefy nodes, fat nodes, because every one of these nodes includes 4 NVIDIA A100. So it's the latest generation of GPUs from NVIDIA, and is hosted by AMD EPYC Rome CPUs, also 2 sockets in this case. We have already also upgraded the InfiniBand network here. So instead of EDR100, we have HDR200, so giving 200 gigabits of network performance per link. We do have quite a lot of links, as you are going to see in a bit. And the topology which we chose is not fat tree topology like on the Joules Cluster side, but on Joules Booster we use Dragonfly Plus. All in all, this gives us 73 petaflop per second of double precision theoretical performance, and it ranks us in last year's list as the fastest machine in Europe, the 7th fastest in the world, and the most energy efficient supercomputer on the among the large-scale systems. I think this is about to change on Monday when the ISC in Frankfurt starts and the new top 500 is being presented. Let's see who then wins those respective slots here. I don't know. Maybe we are still lit. The booster node looks like that. So this is a system which is installed by Atos. So it's about Atos build Sequana XH2000 system. We have those AMD EPYC Rome 7402 CPUs on 2 sockets. That's in the picture, the red stuff there. We do have 2 sockets. Each socket features 24 cores, and each core can do 2-fold simultaneous multi-threads. So in total, we can provide 96 threads. We do have in total 512 gigabytes of RAM, but this is sectioned to the 2 sockets, and the sockets we operate in NPS4. If that doesn't mean anything to you, I have a few slides on that, because this is also part of our early experience. Then in the center of the right picture, you see the 4 GPUs, the NVIDIA A100. We have the 40 gigabyte version here, and, and those are interconnected with NVLink version 3. On the right side, you see the InfiniBand adapters. Those are 4 per node, so that's quite a lot. 4 Mellanox HDR200 connectors giving 200 gigabits per second. So in total, 800 gigabit per second or 100 gigabyte per node, which is quite a lot. And then you see here at the top in this kind of purple color, or light orange, I'd say. That's the PCIe switch, which is also core to this system because this is facilitating the communication from the PCIe bus to CPU, GPU, and HCAs. Just to focus quickly a bit on the A100, the Tensor Core GPU, because that's what gives us basically 98% of the performance of the system. I told you 4 GPUs per node, and we have 936 nodes, so that gives us 3,744 A100 GPUs, quite a lot. So, but if we zoom in a bit, and that's what the picture here should show you, there is also much silicon on the A100, which is repeating itself. So there is basically a whole hierarchy of things providing the performance of Truth Booster. And comparing the A100 to the previous V100, it is just bigger and better. So there are more streaming multiprocessors. We have a larger and a faster L2 cache and larger and faster L1 cache. We have more and faster memory available. The NVLink is now version 3 and not version 2, also faster in this case. And also PCIe is upgraded to PCIe 4, so that's also faster. So basically, this is a faster and larger machine in any regard. There is also new features coming with the A100. They are slowly being used, so I think the performance benefit comes free, but all the other new features, you need to actually start implementing changes in your code, and we just see people coming up with this slowly. For instance, there's the MIG feature, the multi-instance GPU feature, where you can basically partition the GPU into individual pieces. I think this is not so relevant for HPC environments, but more for cloud environments. But nonetheless, I think there could be also something for not so well scaling applications to be used this feature in the future. Then there is some new cool stuff relating to the shared memory of the device, where you can asynchronously copy to the shared memory already out of your program floor, or you can even also include barriers there. So that's going to be interesting when people finally start using that feature. If we zoom in into one of those multiprocessors here, I hope you can at least roughly see the sketch here. You can see that there is lots of space used for individual computing entities. But you also see that basically in this 4 times repeating structure, there is a big green blob called tensor cores. And yeah, that's so powerful that NVIDIA even renamed the device. So it's not a Tesla A100 anymore, but a A100 tensor core GPU. And yeah, I can understand this, because if we look at the performance which is delivered by this kind of tensor cores, this is yeah, quite interesting. So let's start on the graph here, maybe from the left to the right. On the top side of the graph, you see a linear scale, and on the lower side, you see a logarithmic scale on the y-axis. And you can see if you just look at simple double precision FP64 performance, you only get about 10 teraflop per GPU. That's already nice, right? But if you look at the different graphs, you see that's not really the limit. So if we use double precision tensor cores, those new computing entities on the device, we can actually double the performance to 20 teraflop per GPU, and this then is the number which you also find in the top 573 petaflop per second. But there is also new cool precision computing here, where you can, for instance, use TF32 tensor cores, which is a kind of mixed precision computational engine, and with that you can even go to 150 teraflop per GPU. So that's already nice. But the trend continues. So if you go to half precision, so that would be FP16, and here use tensor cores, you also have this 156 teraflop. But maybe you no, sorry, this then is even doubled. You have more of that, so that in total, using this precision, you can go with the machine over 1 exa floating point operation here. So that's really nice with Joule's booster. So depending on the precision, we break this barrier, right? There is also sparsity features. So basically, if you have an array of data which doesn't have entries everywhere, then usually it would mean, if you use these kind of tensor processing units, that you would waste a few compute resources. But apparently there is a feature on the device which can compress that and then only compute the data where it is actually existing, and that gives an extra boost. Coolest thing, or maybe also most strange thing, is the bar on the right side. So basically, from left to right in the bar chart, the precision is reduced, and we end on the right side with binary precision, so just true or false, more or less. But there is also opportunity to use tensor cores with true or false information, and with that you can even go near to the 20 exa op. And that is really nice. So let's see if anyone can use that. So yeah, long story short, the A100 provides a lot of performance, and 73 petaflop per second is only one way to look at it. Depending on the precision you have, we have much more performance available on the machine. Then each node is connected to other nodes. Of course, this is an HPC machine, and we have basically a two-level structure based on the Dragonfly Plus network. We have an in-cell structure and an out-of-cell structure. In-cell, we have a full-fat tree in 2 levels, and out of the cell, we have 20 of those cells. They are not really aligned in a circle. That would be nice, but the cabinets are in rows. But between those cells, we have 10 links between each pair. I'll have more on this in a second. Then we, as I showed you in the first slide, we don't necessarily think as Joule's booster as a standalone machine, but it's rather the system is called Joules, and we just have 2 modules of Joules. So it's a fully integrated system, and that means we have a shared file system using GPFS. The network between the 2 modules is also shared. We use InfiniBand here, and even the workload management is combined here. So that's Slurm, where you can put out jobs with. And then resource management is facilitated by software by Partech called Parastation, and that's also a bit unique version of Slurm, which is operating here, called Parastation Slurm. Which is an open source forked, and then appended by a few extra functions to make it work with this resource management of the system. And here, my colleague Damian Alvarez draw just all the injection points of the network, and you see large point clouds here. In blue, you see the Joule's cluster system, which is a fat tree. So really many, somewhat equally distant points. And then in green, you see Joule's booster, and that looks really different, right? We have this more hierarchical structure with the cells and the things outside of the cell. I think it's cool to look at nonetheless. You can also see where the connections to the file system are and where service nodes is. So this is really nice to look at it. The beauty of HPC, I guess. So just to conclude this part, the software stack of Joules is also unique or common on both parts. So we use Easable to manage this, and then environment modules with LMOD to load this into the respective users' environments. As core compilers of the systems, we have GCC, Intel, and NV HPC compilers. And we do have GPU-aware MPIs, Parastation MPI, and Open MPI, which both use UCX under the hood. All right, just to give you an impression of the important milestones which we had. So in 2018, Joules cluster was put into production, and then it appeared first on the June top 500 list on place 23. And basically, in this year, we already thought about, well, how could the highly scalable extension module of that system look like? And then 2019, the project planning started with the Joules Booster kickoff. In April of 2020, the installation started. Then in May, we had our first job running on the system, and then in November the production was started, and we were also placed into the first top 500 on position number 7. And basically now, or rather last year, the second compute time period on the system started, and now everything's smoothly operating more or less. I want to focus a bit, as Rajit also alluded to, on the early access program, because that's where we have most of the the data from, the ideas from. So the early access program was a program we set up in early 2020, and we wanted to get or provide the possibility to use Joules Booster for early science, and also use it to get early feedback from the system. We invited 14 applications from various scientific domains and aimed for applications which could use Joules Booster at the scale, at a larger scale, right? And we used we talked to people which we already knew from Joules Booster, but we also broadened our horizon and yeah, talked to other people. The offer was that they could use Joules Booster before the general access, and our request though was that they need to help us improving the system, and they also need to find for a proper compute time call to get some compute time allocated on the system afterwards. It was a yeah, it was quite an endeavor, and it focused it had many participants also from the system side, from JEC and beyond. So, for instance, together with the colleagues from NVIDIA, I was steering the early access program. We did some GPU optimization, provided application support, and also some system support. Then our colleagues from the application support and the simulation labs helped us a lot. Our POP team also provided expert knowledge there, and for sure we were tightly basically integrated with our systems operations team, so that we had short feedback rounds and could really iterate through issues quickly. And then from the vendor side, NVIDIA, Partech, and others were also involved here. So this is my colorful timeline, which should basically just show a few things which I consider important during the process of Joules Booster. So we started with a few loose GPU optimization before the system was there. And then when the first node was available, we tried out how is it performing on the A100. So it was really the first time when the first node of Joules Booster was installed in the machine hall. It was really the first time that we also could access the A100, because we were the first and it was a tight schedule. But then soon there were a few more A100 installed in the machine hall, and then we tried also how well the system would scale, or the application would scale. We held additional events, like already at the end of 2019, we started a GPU seminar to talk about certain applications and also certain performance programming models on the GPU. We did GPU hackathon and quite a cool promotional video, which we presented. Yeah, so it was really nice, a nice time. We had also good feedback from the applications, and this is now just more for reference, the list of the applications. I also put in how they are using the GPUs, like with libraries or with OpenACC or CUDA-C. So this might be interesting for you if you revisit the slides. I don't have too much time to go over those slides here in detail, but I have a few, like a lot, performance details at the end of my deck. Yeah, if you have the slides, you can also visit the link here, and you can learn more about the details on each application, what the science case is behind that, and people involved, and all of these things. But I'm here to present more early experiences, and I want to start. I want to do this twofold. So first, I want to present the system-related experiences, and then the application-related experiences. For sure, the system-related experiences are kind of inspired from the applications, because the applications have an experience, then we find this out, and then sometimes this relates to the system, and this is what I'm about to show you. So this all started with feedback during the early access program. So here we had a few issues which we were able to resolve. Yeah, I think by now all of the issues were resolved. Like we had performance fluctuations on individual GPUs, which were probably part of cooling. Then on a node, also thermal, and then on the network, because there were some firmware which needed to be upgraded or something like that. OpenMPI at the beginning wasn't really suited for our setup, but that changed quickly. Nickel the same, so we were able to find a few bugs, and one was in Nickel, this transportation library from NVIDIA. And the HPC Fortran had a few compiler bugs, which you are for sure finding when you look this deep into applications and trying to optimize the performance. UCX, which is the base layer for Parastation MPI and OpenMPI, has quite a few configuration parameters, and they can be tuned well or not so well. At the beginning they were tuned so-so, but now they're tuned good. But that's also something you need to find, and you need to find your optimal parameters for your installation. Then we had quite a nasty bug on the firmware of the PCIe switch. So the PCIe switch was for the first time also installed in our system, and yeah, it was a challenge. And yeah, there are more of these kind of things, but this is just for information. So we found also a few peculiarities, I would say, to call them, you need to make sure that you are using the right software versions, right? So if you use just by switching from UCX 1.8 to 1.9, you could improve your performance of your network performance by 20%. But this is something you need to figure out, right? And there is peculiarities related to the AMD CPUs and the NUMA domains. Peculiarities regarding PCIe switch, GPU, device affinity, and the network. And I'm going to show you a bit of those now in the next slides. So, but we need to take a step back, and because I'm not sure how well you are aware of the current AMD CPU design, I want to just quickly go through it. Well, the most relevant bit for us. So just to remind yourself, juice booster features an AMD EPYC Rome 7402 Zen 2 CPU. It's one of the smaller ones, so we do have 24 cores only, operating on two times. So we have 2 sockets of 24 cores, and each core can do twofold simultaneous threads. The way AMD builds those chips is as a multi-chip module, and that means it has many building blocks and many hierarchies. And the first level of this hierarchy are cores. So here shown in this blue tone, the CPU which we feature has 3 cores, and those cores are in a building block called a core complex, CCX, shown here in this purplish color. They do share an L3 cache, and this becomes important later on. In theory, you can see that there is a faded 4th square there. In theory, you could also put a 4th core here, and the more beefier processors have this, but we wanted to have 48 cores here for the system, so we used the version which has only 3 in the CCX. So now the hierarchy starts. We do not, so then they put onto the chip, they put 2 of those CCXs, and they combine this to a CCD, so the core complex die. So that's here the next level. In theory, no, that's you now could place 1 or 2 CCDs on in what is called a quadrant. The beefier processors would have 2 quadrants now. We also have those at JC, but here for Joules Booster we only have 1 quadrant. So for our case, the quadrant and the CCD are the same. Then, because we have this multi-chip design, quadrant already suggests that there is 4 of these, and indeed 4 of these quadrants form 1 socket, and they are operated, or they can be operated in different ways to expose the hierarchy to the system. And the way we choose, and we think this is also the right way, is to operate them in a way that it exposes 4 NUMA domains in the socket. So we do have here now 1 socket, and actually in our system we do have 2 sockets, but here I just show you 1. But the hierarchy goes a bit further. So between those quadrants, there is a I/O die, which is actually built in a different nanometer level. Quite interesting. And this one is facilitating the connections between the quadrants and also the connections between outside. Also, the memory channel, the RAM is attached through the I/O die, but rather the memory channels are associated to each of the quadrants. So there is 8 memory channels per socket in total, but there is 2 per quadrant. And all of those things are important. So it's a complex topology, and I want to give you an impression why this is important here on the next slide. This is what we call our link test. It's usually a test which we use to send ping pong messages in our InfiniBand network between nodes, but you can also abuse it a bit to send ping pongs between cores. So now here, each line is sending a message, is relating to a core, and each row as well. So you see really this structure where one core sends a message to another core, and from that we note down the bandwidth here. Yeah, you can see absolutely those CCXs, so those 3 cores which are sharing an L3 cache. You can also see for sure the sockets, and also if you study closely, you might also see some other patterns here. So in any case, this makes the structure of the system very prominent, and also shows you that placing your threads on the system is quite important. If you have an L3 using application because you've tuned it that way, or by chance you're reusing data a lot, we recently saw a 30% performance increase by just placing this application properly onto our nodes. Yeah, so this is easy improvement, but you need to be aware of that. Then relating to the memory channels, we do have 2 per quadrant, right? And this then is kind of important how you place your threads throughout the whole socket. And here I ran the stream benchmark, which I guess you're all aware of. And I used the OMT places definition as shown above. And this basically creates one place. And then it, for a certain amount of threads, in this case 12, 24, 48, or 96, it distributes them a bit through the system. So stride 1 means it packs them closely together. Stride 2, it means it takes every other core. Stride 3, every third core, etc. And you can see that if you do this wrongly, let's pick here, the upper left corner, then you place all 24 threads onto the first socket and fill those physical cores, let's say, tightly together. This doesn't give you good performance. The best performance actually is the one to the right and to the lower right of it, where you have stride 2 with 24 threads. So before, sorry, I was saying that was only 12 threads. So you even use only half of the first socket. So here you use 24 cores, And by using a stride 2, you only fill up every second thread or core on a socket. And this really gives you a performance here for the triad benchmark of over 300 gigabytes per second. Yeah, so also for memory intensive applications, even if they are not using L3, it's quite important to use the proper placement. But it continues. So it's not only the L3 and the memory which are important, but it's also the rest of the I/O die, because the PCIe Express bus is also connected via the I/O die. And so this is also to some extent exposed to some kind of hierarchy. And yeah, you can maybe already think where this is going. So on the right side, you see 2 sockets, each with the 4 quadrants, and then the memory is attached here as well. And I've sketched things. And now if we look at the LS Topo view of things, this is getting complicated. But one thing I want to showcase here on the right side is that the PCIe fabric or the switch is only connected here to NUMA node, what is it? 4, I think. Yeah. And this is the important bit. If I go back again, you can see that some of the NUMA nodes are without any of these largest hierarchies, and some are with. So, and this is exactly how it's built. So the PCIe lanes are only connected to one of the quadrants. So there is 2 quadrants per socket which don't have any quick direct PCIe connection. And for sure, that means that you have true GPU affinity only by half of the chiplets. Yeah. The impact, I think, is quite low, because the quadrant-to-quadrant interconnect is quite high. But anyway, it's some added indirection. This is not only true for the GPUs, but also for the InfiniBand adapters. They are also connected through the PCIe switch, so they are same thing is true for them. So now let's talk about numbering. So the numbers of those things are also quite important, right? So if you want to use them, you need to use them by a certain ID. So what are the IDs? Maybe you want to now guess the numbering. Probably if you don't know it, it will be impossible because that is the numbering. So basically all odd numbers are the ones which are connected to some PCIe device, and the even numbers don't have a affinity or a further affinity. So right, it's 1, 3, 5, 7. Now GPUs also have IDs, right? But yeah, GPU is not attached to NUMA domain 0. That's impossible because that's the one which is far away, right? So do you want to guess that numbering? 3, 2, 1. So that's it. So the only thing which makes sense here is that GPU 1 is connected to NUMA domain 1. The rest is totally up in the air. So you need to come up with a affinity table where you specify how NUMA domains, GPUs, HCAs, and then eventual MPI ranks are distributed to each other. And that's the one here. You might see that basically everything fits but NUMA domains. And this is not by chance, but a bit by our design. But before I talk about that, let me just quickly give you now again this full kind of picture of our node, which also has again the numbers in here so that you can revisit how things come together in the nodes. Okay, so the affinity and the numbering. So as you saw, everything makes sense except the NUMA domains, and this is by design because we changed a bit how Slurm distributes tasks and matches the node topology. Our recipe here for a GPU system was that we use GPUs first and only CPUs second. This is, I think, not what you would do traditionally. You would first look at what CPU core you want to run on and get the close GPU to that, but we do it the other way around now. The user doesn't know this, but this is how it's done in the backend. So an example Slurm task distribution for 5 tasks would look like that. First, for the first task, we use NUMA domain number 3. Then we use for the second task NUMA domain number 1, and then etc. etc. And only when we have used 4 NUMA domains which do have the affinity to the GPU, then we start using the NUMA domains which don't have the affinity to the GPU. If you want to have more than one core, you can do this with the usual Slurm facilities like CPUs per task. In this case here, that was only one core, but you can just say more. This is done with CPU affinity masks and environment variables. And yeah, CPU affinity masks are a neat thing. I was quite an affinity mask novice before Joules Booster, but now I know more things, and I fear that people also now need to be aware of those things more and more. So we did a few things to that regard, but first let me talk about those affinity masks. So our Slurm version is called PS Slurm for Power Station Slurm. Sets the CPU affinity mask by looking at the GPU first. So it looks like that. So the example from before looks like that. It sets those 4 masks, and in case you are not as good with hexadecimal numbers, I am also not as good, so I always need to convert them. There is here the conversion table, or the conversion representation. So here, that's the binary representation of the hexa mask from before. I omitted the hyperthreads to make it easier to view, and you can really see that here now there is a 1, which is on NUMA domain number 3, and this one will give you the first core of NUMA domain number 3, and that one will be used by GPU number 0, which is the one close to that. And then for the second task, you have a different affinity masks, and in this case, you use the first core of NUMA domain number 1, and this continues like that. If you were now to increase the CPUs per task to 2 here, now this is a bit shorter, you can just see how this here the affinity mask also changes. Cool. So this is how the CPU mask is generated. For the GPU stuff, we are relying on the environment variable from CUDA called CUDA visible devices, which is also set to the associated GPU. So I've shown you the mask before. So those are the exact same masks, which are for the third and the fourth, for NUMA domain number 3 and for NUMA domain number 1. And we see now that we do have a we do have here the rank number 0, which gets CUDA visible device number 0, and rank number 1, which gets CUDA visible device number 1. So this is how the affinity is done. There is one special case which we came up after some machine learning people complained, is that if you only launch one rank on the node, then we say, okay, probably the application is trying to handle GPU affinity on its own, and we just give all the 4 GPU devices to it. It's rolled out quite freshly, so we need to see how this actually turns out. Yeah, you now learned a lot about GPU masks and CPU masks, and this is a bit complicated. So we wrote in a bachelor thesis, or as part of a bachelor thesis, someone wrote a pinning process simulation tool where you can really try to get those configuration either with high-level Slurm features or with low-level masks directly. If you're interested in this, I also wrote a small Python tool to visualize and generate those masks. And for sure, there is extensive documentation online where you can just read up on things. So those are links. If you have the slides, you can click on them. Now zooming out a bit, the Dragonfly topology is also a bit of interest. I just wanted to mention this now for completeness. We selected this as a good way to balance certain factors like the space which is needed, the investment for sure, and also the performance which is available. Because doing this in a full-fat tree would mean much more links, and this is more of an investment. Yeah, we are still learning the implications of this kind of a topology. It's the first time we deploy a Dragonfly Plus network, but just to give you the full view here, this is how it looks. I will not go into detail on this one, but maybe on the next one here, this is how the cells are interconnected with each other. There is 10 links between each pair of cells and 10 links per cell to the Joules cluster. Here I'm just showing you as an example a few of those. There is the cell number 20 is not filled entirely with compute nodes, but there is gateways for the I/O subsystem. And yeah, the one thing, so basically, if you look at the in-cell topology, this is a full fat tree, and this is what people are used to. But this one now gets sparser if you move out of the cell and go back into another one. And this is where people need to get more used to. And yeah, here this is the form here to calculate the bisectional bandwidth between those n cells. It's a bit strange because you take the floor and you need to halve and then square. But yeah, this is the way it is. But this is yeah, as you are going to see in a bit, somewhat harder to understand from an application point of view. Yeah, here on the right side, this picture is not full. Just because it's so beautiful, I have the full picture of the connections now here. Well, each set of 10 links is one line. If we would also now put 10 lines here, that would be a lot. Yeah, because this is a complicated system, we have interactive job reporting tools. The main one here is called LLView. It's a online tool which has different views. So here you see the system overview, where you can see here on the upper side boxes for each GPU, and on the lower side you see how jobs are scheduled on the system. So you see that here there is a user 029 which is scheduling a large job for a long amount of time and blocking quite a few of those. These are pseudonym or anonymized data, just to show the things. There is also a job focus version of this LLView tool, where you can click on your job and you see a few metrics, and you here see, for instance, on the lower half, GPU metric graphs, or yeah, for the memory or the usage. That is cool, but even cooler is a new feature which the application support has recently implemented. These are detailed PDF job reports, which are automatically generated at the end of your job with many metrics and graphs. And since yesterday, the second version of that is live, and you get there if you click on the on the view from before. You click on there was a quick PDF link, and then you can get this. And I think because there are a lot of cool metrics included here, I thought it's worthwhile to go through a few graphs, even though it takes time. But I think it could be interesting to see what we think is important for users. So this is at the beginning of the first page. There is a overview table where people just see some stats regarding their job. This is not necessarily focusing on the GPUs. There is only here at the lower half. There is only a bit of GPU statistics, but then if you continue, there are many graphs which focus partly on the GPU. So you can see this is here really a GPU because the CPU usage is quite low on the left side, but the average GPU usage is high. And you can also over time see how the GPU utilization is increasing. So at the beginning here, this is only a bit of a slow start, I'd say. So during the first 2 hours, it takes some time until 80% of the GPU utilization is done. You also see how on a so this one here was an average over all nodes, but you can also see how this is faring for each of the nodes or each of the GPU on the node. So each GPU here is a line in this plot, and on the color scale, you can then see the utilization. So this is also cool, and you can already see some patterns. We also show how the file system is utilized here. Again, cool patterns can be seen, which if you know the application, you can study a bit further. In the end, people get an overview how each of the nodes they used are utilized, and you can see that here the lower or the blue boxes represent a bit lower utilization, whereas the red ones are higher. So there is a bit of an load difference. Kind of interesting. All right, so much for the system-related early experiences, and now I want to go over to the application-related experiences, which are also plenty. And yeah, I hope I have enough time to show all of these. Yeah, so a word of caution, many of those things which were really studied on the system might not still being ready. So people are now starting to produce these results properly in a more, yeah, in a more in a less hectic fashion, let's say it like this, and then you are eventually seeing publications from that which are done more properly. But right now, I think it's fine, but there might be some undetected underlying issues here. Okay, I want to first start with an application called SOMA from the soft matter domain. It's a Monte Carlo simulation which simulates kinetics of nanomaterial formation. And the unique thing about this is that it can resolve details at different scales, and even going to lengths of real-world engineering. This is a team which participated in the early access program. They have an open source application using OpenACC, and they already use Joules for a bit of a time. And you see this also here. They are doing this GPU business for some amount of years, and they show that it's really worthwhile to upgrade to new generations early, because then you can directly get those benefits of improved compute capabilities, so instruction sets, I guess, but also from the hardware point of view. There is a few algorithmic changes between, but most of the things were just feature additions. Here on the Y scale, higher is better, obviously. A cool thing is something, and this is now maybe the first performance engineering stuff you're seeing, is relating to random accesses. So this is a Monte Carlo method, so there are many random accesses. But yeah, then when the A100 came out, it came out with larger caches. This is, I mentioned before. And caches are not something you necessarily directly see in floating point performance, right? So when they write onto the box of the A100 that it has 19.7 teraflop of double precision performance, this doesn't include directly the increased caches. But here, SOMA could really utilize those larger L1 and L2 caches by having higher hit rates in the caches. And this resulted in higher double precision throughput. And also the memory, so the GPU memory wasn't used as much. So the knock-on effect here was really higher, was really good. So the runtime of this specific kernel, whatever it is, decreased from 25 milliseconds to 21 milliseconds. So that's already good. And then we, under this impression, they were, so this was measured in a GPU hackathon, and under this impression, they were then able to introduce even more optimization targeting the cache, now knowing that the cache is larger, and could improve even the performance a bit more. This also, the Joules booster system inspired them to work on ways to improve the scalability. And they basically did a meta version of their application where you have parts of your application recalled. They call this the string method. This is a new method developed in a master thesis, I think. And it's a coupled SOMA application, which does, I think, parameters. And you can see that the scalability is much better here in the green plot on the upper right side. More plots, and from a performance engineering side of view, more data I'm showing now on Yuknes. Funny name. It's a quantum computing simulator, and since we have two of those from this unique group, our colleagues from JC, this is the one which deals about the master equation, the quantum master equation, which simulates more the physical realizations of quantum materials. It's quite compute intensive, but not yet really scanning a lot. So it's the GPU version is a bit new. It uses OpenACC, but for specific kernels also CUDA-C. This is really some fresh analysis, and I wanted to take you on the way how we look at this or looked at this application in order to improve the performance. So we started this with one of the tools from NVIDIA, that's Nsight Systems, and we instrumented certain ranges of the computational flow with these NVTX ranges. Good thing is that you can then also use ranges on the CPU side to put into boxes and understand them better. And we found out that here for this specific kernel, XY kappa TR, the multiprocessor utilization is actually quite low, and also the memory utilization is quite low. So everything's low. Why is this? So we changed the tool to NSI Compute. You already saw a quick screenshot from NSI Compute in Soma, but now here is more about this. And the first metric which you can see when you launch this application with your instrument or with your profiled kernel is this GPU utilization as the speed of light. So you can never reach the speed of light, but you can try to come close, right? So, and we really see what we've also seen before, the SM utilization and the memory utilization are low. So what's up here? Is it latency board? Where come the other stalls? Is there not enough parallelism? What's up there? If you scroll down, you can then see further things by studying an included rootline model. So here you can see the performance versus the arithmetic intensity. And you can see that here we are quite below the roofline. So this is a logarithmic plot, so it might just look like a bit below roofline, but it's actually 60% below. So it's probably latency bound, but then there is also some guidance shown as a tip here, and I quoted this here, and they say that it's typically an indication of latency issues, and we should look at the scheduler statistic and the warp state statistic view. And this is further down in the application and quoted here. You can see the scheduler and warp state, and you can see that there is many non-eligible warps, and that means that there are warps which are basically ready for flying, for execution, but they don't have usually the data yet, or for some reason they are blocked from actually being executed. And that results also in many cycles per instruction. So we have 128 cycles per instructions, and that is not a good thing on a GPU. This is much too high. Elsewhere, you see that there is also many global load throttles and long scoreboard stalls, which also indicate that there is something going on fetching the data, which is non-optimal. So there is a other view which can guide you now, and that's the source view, which I'm changing to now. This just puts in context, and I hope it's not too small, the source code and the basically says, so that's the instructions, the machine instructions, or as close to the machine instructions as you can get. And it also prints you these nice register views here, where you can see how full a register is. And there's also some tooltips which are there. And basically, it shows you where the stalls come from in your code and what the stalls are in the tooltip as well. And yeah, if you study this more closely, you can see that that you access the data in a non-optimal fashion. And you have these four for loops here. And yeah, if you look at this, you can see, well, the outer loops should actually be the inner loops, and the inner loops should actually be the outer loops. I mean, this is no trick. This gives you also performance on the CPU, so this is known for a lot of time. But if you are an application developer and not on a CPU, you can sometimes get away with this, and because your flow of thought and the way you program your application, that's more natural, right? But for the GPU, this will actually hurt you in terms of performance. So they started reordering the loop, and now we can use NSI Compute to compare the new version, which is loop changed, to the old one. So we have the previous as the baseline, which is now also available in the tool as reference here in green, and we can use it to look at the new optimized version. And you can directly see that we improved the overall GPU utilization by a lot. We also on the roofline moved much higher here, so that's the new point. We also improved those scheduler statistics, so there is now there was nearly 9, or there was a bit more than 9 active warps per scheduler. This is good. There are much less or there's, let's say the other way around. There are much more eligible warps here. So that's all good statistics which we've improved. And it tells you that we've improved things also in this percentage way. So in total, we've increased the runtime of this, we've improved the runtime of this kernel sixfold, resulting in 35% runtime overall of the application. And for this, yeah, that's certainly worth it, right? Yeah, so this was a typical flow how we tackle optimizing applications. But I'd like to show you a bit other things, maybe, and also some other tools. So one application which we've already worked on during the last months before Joules Booster, it's called ParFlow. It's a numerical model for groundwater and surface modeling. It can model all the hydrological processes and can even be interfaced to other atmospheric applications. It uses CUDA, but it uses a cool strategy by having an embedded DSL, which you can, during compile time, switch between different backends. And yeah, here the application owner, Yarrow, started porting 2 years ago, I'd say, or two and a half, and by now he's reached a in a node speedup of 29-fold. He gets good improvement by using a memory pool. So we saw when we analyzed this, we saw that he had many individual memory accesses, which were giving him a lot of latency. And then the idea was to use the Rapids memory pool, and yeah, just once allocating a lot of memory and then having this internally book kept. And this gives an extra boost. And now more from a scientific point of view, Yarrow can solve larger problem sizes, or everyone using ParFlow can solve larger problem sizes on a per node basis. So even though they have this embedded DSL, they only included CUDA. Now the next step, they are working on COCOS to also focus on different backends, maybe also targeting different GPU architectures. They're not there yet with the same performance like with CUDA, but I think they might be getting there. Also looking at weak scaling, they see good speed up. So here they usually achieve 26 speed up in the long run over hundreds of nodes. We had also a POP performance assessment done by one of our colleagues, Ilya Zukov, who is part of the POP Center of Excellence 1 year ago. You're looking here with Vampire onto one node because it's easier to visualize, and 4 nodes. You can really see the call stack, and you can see this refined grid here in the middle where it gets closer and closer, or smaller and smaller, and then it grows again. So that's the way ParFlow is working. You can also see the MPI connections here within the node, right? So you can study how the flow in the MPI is running. And if you look at this now here for not 1 node, but 16 nodes, you can actually also see that there are some late senders. So they are posting the MPI receive much before the MPI send is issued. For ParFlow, this is not too bad, but as you are going to see on the next set of slides, there is different applications where this actually is sorting. And this is one of the applications that's called YUX. It's another quantum simulator. This time it's a universal quantum computer simulator, so it's much more theoretical than the one before, but it's also much older and extensively and longer developed. So it's really a production grade code who is now using CUDA with CUDA Fortran. They can resolve up to 42 qubits. Here just the numbers for 40 qubits. So it needs 512 A100s, and each quantum operation in the end needs to update all the states, and that means 8 terabyte of memory is being transferred. And you can really see this here also on the plot. There is much MPI time visible. The weak scaling is shown here on the green part. In the purple part, that's strong scaling, so using 40 qubits, but it's increasing the amount of GPUs. And here a thing which is basically not so well understood at the beginning, or wasn't so well understood at the beginning, is why if we double the GPUs amount, why is the MPI communication amount not half, but reduced even further. But it's exactly through the Dragonfly topology. But this is something which is not from the get-go accessible to the user. So you need to really understand this. Yeah, this behavior continues. So here it's just a plot going to even more GPUs. So 2048 GPUs and 42 qubits. And yeah, MPI here is indeed really the limiter. And this is why we had to look at the MPI profile first with inside systems here again. So you know the tool by now, and you can see here up top the kernels. And there is a gap between this kernel and the previous kernel. And yeah, the gap is taken over by MPI send receive. And yeah, it would be cool if we could get rid of the gap. So even without actually knowing what's happening, can we do anything about this? And indeed we can. We suggested that maybe he can overlap the send receive with the kernel computation. For sure, this is also an easy trick from the book, but it needs to be implemented. And people might not think, because, hey, this is just a short message. How much time can it take anyway? But you're using a GPU, so how much time can this take anyway? Yeah, so the application developer implemented double buffering, and with that was able to overlap GPU kernel calls and the MPI calls. And for this part of the iteration, this gave him improvement of 30%, which is nice. It's a good improvement. Yeah, just fresh from yesterday, I have a few plots of just a few highlights. We haven't discussed this really, but a few highlights with the first analysis of this application with the SCORP stack. Here now, this is 2,448 GPUs shown in Cube. You can really see how, yeah, also a tool like Cube, which is traditionally used for CPU things, can also be used for GPU. Yeah, then we can also here see those late senders. In this case, it's Galaska. And you can see, if you were able to read these small numbers, that there is indeed also here a certain issue regarding the late senders. And on the right side in the box plot, you can see that, you can see that each MPI receive waits, I think, for 5 seconds in average to for the MPI send to be issued. And this is something we need to work on. This was before we implemented the double buffering, so that might be a bit elevated, might be a bit reduced by now, but we still need to investigate this further. Yeah, you can also look at the using Vampire, you can look at the MPI flow. In this case here, it's a smaller case, but this is easy to look at how the MPI connections are drawn. Here you can see that at the beginning of the application, most of the time GPUs are talking to GPUs from within the node, but this is by design, so this is why this application is so efficient. But then, yeah, when time progresses, and this is now a snapshot more to the end, then the communication pattern is a bit different. And yeah, you can get those nice visualization here. And I guess knowing the application more than I do, you would be able to understand why this communication here is looking like that. Okay, just a few other snapshots from other applications quickly. So we do have a lot of quantum chromodynamic simulations in Jülich, and one which participated in the EarlyX program was this ETMC, the Extended Transit Mass Collaboration, which studies the flavored signal structure of hadrons. They have, I think, their first publication out by now. They use CUDA a lot, which is the NVIDIA QCD library. Yeah, and the cool thing here, which I found nice, is that they were able to utilize Roots Booster a lot, and just using half the amount of GPUs compared to the next best system, they were able to reduce the time to solution a lot. So this really gives them good performance. The spread here, that gave us a bit of worrying. It's for sure also existing for the other system, but yeah, this is what we are currently investigating for a system view of side things. Then slowly come to the end. We by now have also applications running and producing first glimpses of results, not participating in the early access program, which are called now others. And the first one here, just to give you an impression, is called DASO, which does distributed training better than Horobot. Yeah, and unique is that they see this 25% improvement by just cleverly using the communication pattern. And then closing things up with the beginning where I mentioned these half precision tensor cores, there is a large-scale simulation of ab initio molecular dynamics by colleagues from Paderborn University. And they what's unique to their application is that they can use mixed precision of FP16 and FP32. And yeah, remember that we are on the top 500 with a theoretical peak of 73 petaflop, but they actually measure now in their application up to 320 petaflop per second. And that's really cool because that's just by using those tensor core features on the devices. So we are eagerly waiting to understand more or hear more about this application because they were not really in contact. I really got this from the archive. Yeah, so let's see how this turns out. And maybe there is also people using other tensor cores on the machine, which can even go higher there. So to slowly conclude and also give a bit of a summary. So I presented to you Jules Booster, our system with A100 GPUs and plenty of those. We can reach 70 petaflop per second of double precision performance or more if you go to lower precision. And we have a accumulated injection bandwidth with all the HDR200 links of nearly 750 terabit per second. We started in November and have experienced most of the user experience through the early access program. But now first results are also incoming, and even the second allocation period started. I showed you a few of those tools which are most important for our work. That's Nsight System, Nsight Scorpy, the whole Nsight Compute, and the whole Scorpy stack. And I think in Bernd Mohr and Michael Knoblauch's recent article, there is a great overview. So if you have the slides, click on this. From my now rough perspective, important models for studying the GPU or yeah, this is a GPU utilization because it's so easy to grasp. The cache hit rate is something which we found useful. And then for sure, the various incarnations of roofline models. Yeah, there's this cool paper, as I guess you will all know from Ding and Williams, about the GPU roofline. So this brings me to the end of my slides. Just while we maybe talk, I want to leave these acknowledgements here because this talk was helped a lot by my colleagues. But anyway, this is it, and I'm open for questions.
Okay, thank you so much, Dr. Herten, for the really interesting keynote speech. Actually, me myself, I have tons of questions, but I will let like other participants. Either you can write the questions in the WUFA interface, or you can just raise your hand and later I will let you unmute yourself and ask your questions directly. Okay.
I'll hop in real quick here, Connor. Since I can unmute myself, I'll just do it. So I do have a question about the LL view that you pointed out earlier, Andreas. Is that
sure.
Was that a bespoke software, or was that something that was provided by like a vendor that provides some hardware?
No, that's from us. So that's already developed for a lot of years in Jülich. It's open source. No, I don't know. It's freely available. I think it's open source. I'm not sure, but this is the website. And I think you will not yet find this cool PDF performance reports there because they are just like rolled out and tested. But I think soon that will also be part of that.
Okay.
But yeah, it's really cool.
Did you find that it was difficult to like adapt the new architecture to this visualization, or I guess was it built so well that it handled all this data?
Yeah. So this was done, or this is done by my colleague Wolfgang Frings, and I think he's already, when he heard of what the rough architecture of Joule's Booster was, he started already implementing things. But it looks very similar for different systems. So I think it's very adaptable, and it's also used by other centers. So I think from the way it is made, it's already quite easily adaptable.
Thank you.
Okay. I want to ask my questions about, do you have any best practice that for managing this kind of variety of machine learning applications? Because as I know, they have their own peculiarities, and it's also mentioned in your paper, in your presentation, that there is a problem with NCCL and there is this GPU fluctuation. Yeah, that's like.
No, but we don't have yet a best practice guide or even a rough version of best practices. No, it's really hard. So I think from an HPC point of view, MLDL applications are hard to deal with because they come with a very unique stack. They usually involve Python. This complicates things further. Yeah, and then some of the DL developers are not really developers, but more users. So they don't know, they write a Python script, which they know what it does, but in the end, they don't know what function is called under the hood, or how does this function relate to that function. So they are maybe a bit further away from the software than a usual application user is. And yeah, those are some of the complications which we see. We are trying to, so at the beginning, we were a bit hesitant to provide a point of entry through containers, because we fear that containers will be built non-optimally, and then they don't provide the performance which we can offer. But by now, we see that it's probably the better way to give people, or MLDL people, access to our system through containers, because this is just the environment where they are more used to, and yeah, those other things. I wanted to mention we are releasing a paper on the AI capabilities of Joule's Booster, where we also have a bit of those things in. It's not really a best practice guide. It's more like an overview of what's possible and some first use cases. That's going to be released, I think. So it's presented during a workshop today as well, and I think next or the week after it's going to be released.
Okay. Yeah, that's interesting. That's also like during the first day we were talking about the reproducibility, and this is like an open science questions for the
Absolutely.
MLDL. Yeah. Okay. Anyone? I don't want to hog all the question slots for myself. Regarding this, do you see like more machine learning applications like inside the Joule's?
Yeah.
More, like in general, more and more, or something like that?
Yeah, absolutely. So we see people coming in. I think this is to some extent driven by the capabilities of the GPUs. But yeah, it's so large scale deep learning is still a bit of a a new project, I would say. Probably doesn't make it justice, but it's people who can use GPUs on this larger scale are rare. It's changing for sure. Yeah, and we're seeing more and more people coming in. Absolutely. We have dedicated support staff now for AI, so they are also quite busy. But this is how you see that it's not just a corner of HPC, but it's really a different flavor of computing.
Okay. We still have time here. I literally want to ask a lot of questions. But so, I think the first part of the slides, I see like a lot of the tensor unit. Like, do you see like whether it highly utilized or not, or like what kind of applications that will get like the most benefit of it?
Yeah, this is a good question. So tensor cores are around already for 4 years. They were beefed up a lot for the A100 last year, but in the V100 you had tensor cores already. We are trying to actively let me go one step back. So they are usually used, and I think they're built for deep learning application because they have so many tensor contractions that really maps well to those computing entities, and that's why they are there. But in the end, it's just a matrix multiplication of a certain size, of a certain precision. And in HPC, we do have matrix multiplication, obviously. And yeah, but traditionally, the hard thing is that this reduced precision is not something which people can easily adapt to. They are happy with their FP64 precision. They have numerical stability, which they need to regard. They want to reproduce the results. So if you somehow change, even in an iterative algorithm, if you somehow change the intermediate precision to something else, you will have different results. They're not necessarily wrong, but they are different. So that's a bit hard for them to find out where to go. But yeah, the hardest thing is to talk to the people and find out really at which position they could now actually use those tensor cores. You cannot use them just by multiplying two variables, but you need to actually use API calls to things in the CUDA API to make use of this, and that's what makes it hard. On the other side, it makes it a bit easier for others. So what we are always preaching to please use libraries. And people who respect this, they just need to flip a switch for the library, provide a flag, and then they can use reduced precision and will automatically use the backend libraries called to this reduced precision functions. But yeah, this is not the majority. Maybe it's half and half. It's not all of them. Yeah.
I see.
But so from our perspective, we would like to have much more people using those tensor cores because it would be amazing, and we have so much performance available
there. Like, have you experienced like using the vector cores, and then like, is this similar or different? Or I'm having like difficulty to understand like what is the difference in terms of the performance that I will see between like this using the vector processor unit and this tensor processor unit.
Okay, so that's wait, let me go to the slide. So that's this slide, right? So you see, if you're not using these tensor cores, you will just use what's blue here. So that will be your maximum performance. Wait, I can try to zoom in. Does it work? Oh,
yeah, it works. I mean, like, it's okay.
Okay. So you can only use here, that's 9.7. That's, I think, twice as much. So FP64, 9.7, FP32, it's 19.5, and then you have a bit more for other reduced precision, but they are not using tensor cores. So in blue here is not tensor cores, but as soon as you flip the switch basically to use tensor cores, you can use much more, and then you can also use reduced precision tensor cores, and you can even use reduced precision tensor cores with this sparsity feature, and that really is a lot. That gives you a lot of performance.
Yeah, this is really interesting.
I mean, if you use the right metric, we do have a 20x out machine, and this is interesting.
Yes, definitely. So we are already like in this exascale. It is now.
Depending on the metric, yeah.
That brings me to another question, actually. When you show me, you show us like that chart, like even like in the correct nodes or like in the network, that you can gain like 30% more performance. I don't know. I feel like that's not the good news, like because like the performance is really like fluctuating too much. And do you have any do you see any plan like to make it like much more, I don't know, reliable or like uniform?
No, but let me just quickly go back to that topic again. So you mean this one here?
Yeah.
Yeah, but this was not because of any fluctuation. It was just because we were able to overlap MPI sense and computation on the GPU side. So basically, before we did this optimization, the GPU was computing. Afterwards, we were sending data, and only when the data was sent, we were continue computing. But then the user added this buffering strategy where you could actually compute. Then you put this into a buffer. This buffer was then sent, but during the same time, the next computation was already started. So we just overlapped things, and this is good improvement. And for sure, this is one of the usual optimizations we try to do, because communication and computation can, to a large extent, be separate from each other. For sure, you cannot send before you have no computer, but you can compute, put it into a temporary buffer, and then compute the next step already. And with that, you can, to some extent, hide the additional latency from the network.
Okay, so that's not because of the infrastructure itself, but there are changes inside the applications. Okay, yeah, that's much more reassuring.
Yeah, so here we had some fluctuations between the time to solution. So in the mean, it was 1.4 seconds, but it was going up to 1.8 for certain cases. And yeah, this was analyzed, it was tuned a bit, so the routing was improved, but this is nothing that a user can do here.
Oh, okay. Yeah, that's...
This is what happens, I think, in the early days of a new system. You need to understand how data is transported, what is the right parameters, message sizes, and these kind of things.
Yeah, exactly. And hopefully, like everything can go to the exascale performance, right?
Sure. No, this is what we aim for.
Yes. Okay. I think we are out of time already. I would like to thank you once again. It's a really good presentation. I learned a lot, and I hope like our participants also feel this presentation is interesting and learn a lot from this. We are going to have the recording, but it's after the workshop is done, and I think the whole conference is done. It will be shared in our Permavost website. So thanks again, and we can continue to the next schedule, which is lunch break. So see you again at 2 p.m. if I'm not mistaken. Okay.
Thank you.
Bye. Thank you. Bye.
So, hello. Welcome back, everyone, to our paper presentation session. We have 3 very interesting papers to present, each one with around 20 minutes presentation plus 10 minutes for questions and answers. We encourage you to drop any question you have here at the Zoom chat or at the Hova platform, either at the chat or at the questions tab. So we will start with our first presentation, which is the paper entitled TOP, a lightweight tool to unveil parallel efficiency of large-scale executions. by Victor Lopez, Guilherme Ramirez Miranda, and Marta Garcia Gasula, all from the Barcelona Supercomputing Center. So I'll invite you now to watch their presentation.
So I'm getting the sharing up. One sec. Sorry, guys, it was working. Let's see if I can't do it that way. Let's see if this. Can you guys see it? Is that...
Yes.
Okay, and you can hear as well? Or can you hear now?
We are not hearing Connor.
Dang it. Okay, sorry. You know, we just verified that this worked in our other Zoom room, and then of course, whenever you come into this one, it all breaks down. That's just the way it goes, right? Go from sharing. Okay. Let me go back. All right, so you guys, can you hear that now? Were you able to hear it for a sec?
Connor, I think your volume is very low. Can you increase it, please?
Oh no. Okay. Yes. Well, I can't. Oh wait. Cannot. Wait. Sure sound. Okay. Okay.
Hello, everybody. Thank you for joining. This is Marta Garcia Gasulla from the
Now you should be
Barcelona
able to hear,
Supercomputing
right?
Center.
Marta, can you not?
I also would like to
Thank
thank
you.
the organizers for putting together this workshop, and especially also my colleagues, Victor and Guillem, who helped me do the work that I'm going to present now. The work that I'm going to present comes from two different projects joining together. So from one hand, we have POP, the Center of Excellence for Performance Optimization and Productivity. POP offers services to the users and developers of HPC applications in Europe, analyzing their applications to find the problems and the bottlenecks for the non-scalability of their applications. POP also has a common methodology, and it's based on the idea that once we have an execution and we consider an execution a real run with an input set, a code running in a cluster, based from this execution, we can obtain traces. These traces is like an X-ray of what happened in the execution of this application and are stored in files that we call traces. We can apply the efficiency metrics designed at POP, which are like a blood test. In these efficiency metrics tell you where the main efficiency loss in the application is happening. But this is not the end of the journey. Based on these metrics, the analyst can know where to look. Then, using other tools that we have available to the project, we can analyze in detail where these efficiencies are being lost and which are the sources of this efficiency loss and why. So after this detailed analysis, it's when we are able to provide a diagnosis to the client. On another hand, we have DLB. DLB is a dynamic library that intends to improve the performance and efficiency at the node level. It's based on shared memory. It means that it can only be applied inside a memory with shared node with shared memory, and tries to coordinate with the different layers of the software stack, always trying to use common APIs so that it's quite transparent to the user. DLB is organized in 3 different modules. LEWI, which is in charge of dynamically load balancing hybrid applications. It will be able to load balance MPI processes that are running in the same node using the second level of parallelism, OpenMP or OMS. Then we have DROM. DROM is it's used to dynamically reassign resources within the node. It can be used by applications or by resource managers that have a general overview of the performance of the node. And last but not least, it's the work that we are presenting today. It's TALP. We wanted to take advantage of the infrastructure that we have on DLB. And we implemented TALP, which is gathering metrics of the efficiency of the application at runtime. These 3 modules are independent. They can work one without the other, but they are coordinated. They can all be used at the same time. So I said that the POP has a set of metrics, of efficiency metrics. These metrics are organized in a hierarchical way, and they have the property that they are multiplicative. This means that any 2 child metrics, when multiplied, give the parent metric. We extend these metrics with 2 additional metrics, the intranode load balance and the internode load balance. These 2 metrics give us the idea if the load imbalance problem is coming from within the nodes and can be improved with LEWI, or it's coming from between nodes and other kind of load balancing measures needs to be taken. They keep the multiplicative property of the other POP metrics. So the key points that I'm going to present is that we will offer a way of obtaining the POP metrics without traces and without previous knowledge of the user. And we present 2 additional metrics about load imbalance. For TALP, it has mainly 2 uses. The one that is used just at finalization, where we gather the metrics at the end of the execution, and the one where we can obtain the metrics during the runtime. The finalization way of obtaining the metrics is transparent for the user. It's intended for HPC users with previous performance analysis knowledge. And it's a way of obtaining just a straight way forward information on the performance and efficiency of your run. The API at runtime, it's used to obtain metrics at runtime, and it's very useful for auto-tuning applications or resource managers that needs to adapt while the inefficiency is happening. So the main question that I get when I'm presenting TALP is if it's this yet another profiling tool, and the answer is no. Here in this slide, we can see 2 different applications. Application A has a problem with load imbalance because the first MPI process has lower work to do than MPI process 2, while application B has a completely different problem. It's perfectly balanced, but it has a lot of MPI communication, adding some overhead. So if you use a profiling tool, you will get exactly the same measurements because they spend exactly the same amount of time in MPI, both applications. But TALP will give you 2 different informations for these applications. TALP will report that application A has a problem of load imbalance, and TALP will report that application B has a communication efficiency problem. How TALP works? Well, imagine that this is an MPI application with 2 MPI processes and 2 threads each one. Once the application reaches an MPI call, TALP intercepts this MPI call through a PMPI and will store the compute time and MPI time based on that. If you are entering or exiting the MPI call, at the exit point, the same thing will happen, the interception, and will store this the total compute time that this process spent in MPR or computing. This is important, just that the information is stored by process, is also based in the number of threads that are active at that moment. So if you span more threads, this is going to be taken into account in the compute time. And there's no communication needed between processes. Every process has its own information. This allows us to that doesn't have problems of synchronization between processes or overhead when you are using more processes. Then at the end, when the MPI finalized call is reached, TALP prints through the standard error the efficiency metrics that it has collected. You have here an example of the output that we get from an application. Additionally, you can use the user can use the API to obtain the metrics during the runtime. In this case, it will call the API, and TALP will give the information that he has stored to the application so that the application can do whatever he wants to readjust its execution. So, and I'm saying that I want to show that it's really easy to use. In the case of using the finalization version at finalization, just getting the information at the end of the application, for very basic users, we just need to set an environment variable telling DLB that we want to use the TALP module and preload the DLB library and then run our application as we are used to do. Just doing this, we will get this summary here. If we are a more advanced user, then we can use the API. To use the API, we need to include the .h file. And if we want to add a monitoring region, we want just to measure one part of the code. If we know very well our application, we know that it has different phases, so we want to measure these different phases separately. Then we define a monitor region by a name. And then whenever we want, we can start and stop it. And this monitoring region will just count the time in MPI and compute when it's inside the monitoring, when it's running inside between the start and stop calls. At any point, we can tell the TALP to give us the information of this monitoring region, and then looking through the different fields of this structure, we can get the metrics. So this can be used to obtain the metrics at runtime, but also to define regions that will be reported at the end. If we define monitoring regions with the API, they will be also reported at the end in case we want to get a more detailed report at the end of the application. So for the evaluation of TALP, we used 3 different applications. We have PILS, which is a synthetic benchmark, and it's very useful for us because we are able to tune different parameters and study in more detail some things. And then 2 HPC applications, CP2K and ALIA. We choose these 2 HPC applications because they have different problems. CP2K is an application with communication problems because it has a lot of MPI calls. So it suffers of the overhead of MPI, having a low communication efficiency. And ALIA, on the other hand, has a load imbalance problem. We use 2 different input sets of ALIA, one which has more computation with a coarser granularity, and the simple one, which has less computation with a finer granularity. This also allows us to see how the TALP behaves with different kind of patterns. The evaluation is divided into main parts. On one hand, we want to measure the overhead of TALP, because if this is a tool that we want to be used in production runs by users, we need to ensure that the overhead is really low. To measure the overhead, we just run with and without TALP, and we measure the percentage of overhead added by TALP. And the validation, we want to know if what TALP is measuring is correct. So that to do that, we compare the metrics obtained with TALP with the metrics obtained with the common tools from the POP project, which is Extrae and the basic analysis tool. To start with the overhead analysis, here we see the different overheads measured with the different applications that I have said. The first plot is with pills. In this plot, we can see in the x-axis the percentage of overhead respect the total duration of the execution. And the y-axis, we have the number of MPI calls per millisecond. The number of MPI calls that has been executed is the frequency that the MPI calls have. This is affecting TALP because every time you find an MPI call, then TALP needs to intercept it at the beginning, at the end, and store the information on how much time has gone from the last call. We see that the overhead of TALP grows as the number of MPI calls per millisecond grows. That when it's 2000 MPI calls per millisecond is almost 10% overhead, but this is quite extreme case. And we also see that when using regions, monitoring regions, the overhead is slightly higher than when not using them. If we say that the acceptable overhead is below 5%, we can say that we can, with TALP, we can rely to run applications that issues less than 100 MPI calls per millisecond, which is, as we'll see when looking at the numbers of the real application, this is quite a high number. So for CP2K, which is the application that has a communication problem, which are a lot of MPI calls, we see that the overhead is below 7%. So we consider that it's quite acceptable with the higher number of MPI calls, which is 768 MPI processes running. This is scaling the application to a high number of MPI processes. The overhead is almost a bit above 6%. We'll see that this means a very low communication efficiency. So that's why I'm saying that even for applications with a lot of communication, the overhead is acceptable. For ALIA, when using ALIA simple, that is the one that has a fine granularity of computations, the overhead is always below 2.5%. And when using the ALIA complex, which has the coarser granularity, the overhead is even below 1%. So for ALIA, we can say that there's no overhead. For CP2K, it's below 6%. So the validation, well, we can tune all the parameters in pills. We feeded pills different executions with different load imbalances. The number below is the load imbalance that the theoretical one that were fed to pills, and this is the load that each MPI process had. So this was the case where the applications was perfectly balanced. We also used different frequency of MPI calls per millisecond. We see that the percentage of error of TALP, of the measures of TALP, is always below 2.5%, even for applications with a lot of MPI calls. With 2000 MPI calls per millisecond is really a very high number. The validation with CP2K. Here in the x-axis, we see the different number of MPI processes and the different efficiency metrics that can be obtained. In gray, then the efficiency metrics obtained with the basic analysis, and in blue with the efficiency metrics obtained with TALP. We can see that for the load imbalance, the efficiency metrics are the same. We also see that there are some columns that doesn't have a measure for the basic analysis. This was because the traces obtained with this number of MPI processes were too big to be processed with the basic analysis. So we were only able to obtain this these values here. And also the two metrics that we are presenting that are not yet implemented in the basic analysis. That's why we have bars that doesn't have a value for the basic analysis. The other thing that we see is that in the communication efficiency, there's a slight difference between what basic analysis measures and TALP. We analyze this in detail, and as we can see, the efficiency metrics of CP2K, the communication efficiency of CP2K is going down drastically, reaching almost 50% of efficiency loss due to communication. This is a high number of communications happening in CP2K. And this is the effect of the overhead when tracing this, because all the overhead is going to MPI, all the tracing overhead is going to MPI. So that's why the basic analysis tells us that there's a lower communication efficiency than TALP, which has less overhead. For ALIA, we have the same thing with the two input sets. Here we have the complex one and here the simple one. We see that in all the cases that we were able to obtain the metrics with TALP and with the basic analysis, the metrics are the same, so that we can validate that the metrics obtained with TALP are correct. And in this case, it's very interesting to see how the pattern of the load imbalance changes from one run to the other, and how the additional load balancing metrics can help us understand better which is the problem of this application. In the complex application, the load imbalance efficiency is going down as we increase the number of MPI processes. And we can see that this is a problem inter-node. So it's happening between, it's load imbalance between the nodes. The load imbalance inside the nodes, it's not changing so much. On the other hand, the simple execution, the simple input set has a very bad load imbalance, but it's always flat. It's not changing as we increase the number of MPI processes. But it's very interesting to see how the load imbalance inside the node increases as we increase the number of MPI processes, while the load imbalance between the nodes is decreasing as we increase the number of MPI processes. So to conclude my talk, we have presented TALP. TALP can work in two ways, just obtaining the metrics at finalization. The POP metrics, it's a way of obtaining POP metrics transparent for the average user without previous knowledge of performance analysis, and they just get the metrics at the finalization of the application. We also offer an API to obtain these metrics at runtime, and this is in targeting applications that are able to auto-tune themselves or to resource managers that want to know how the application is performing. In general, the overhead added by TALP, we think that it's acceptable as it's below 5% as long as you are issuing less than 100 MPI calls per millisecond. And our idea is to improve this with our future work that because we can detect this. We can detect zones with a high frequency of MPI calls and just disable TALP when we detect a zone that has a high frequency of MPI calls, to avoid adding overhead to the execution. The validation has shown that the metrics that are being measured by TALP are correct, even with low granularity situations. And we have also seen that we have also presented two metrics to understand better the load imbalance. And we have shown that they are useful to determine the best approach to address the load imbalance of an application. Thank you very much for listening, and I'll be happy to answer any question that you have.
Thank you, Marta, for your presentation. Are you there to answer the questions?
Yes, I'm here.
Hello. Thank you.
Hello. Thank you.
So we don't have any question from the audience yet. I will give the audience more time to text the questions. And in the meantime, I will ask mine. So thank you for the presentation. I found TALP a very interesting tool, and I really appreciate your efforts to consider the usability by people with or without knowledge of performance analysis. And you presented that TALPUP can achieve an overhead of fewer than 5% when we have less than 100 MPI calls per millisecond, right? So this is a very low overhead, but like considering the benefits of the profiling, but I was wondering where TALP is compared with other existing profiling tools for online or offline profiling.
So we haven't compared with other profiling tools. We have compared it with tracing tools because we consider that the information that we get is closer to the ones, you get more information than just profiling because we are able to compute the metrics. So it's one of the things that we saw, for example, is that it's much lower than tracing with Extrae because the amount of information that we gather, we try to be very lightweight. We just get the information at the beginning of the MPI calls and at the end, trying to keep it at the minimum. We improved some things also when handling the different threads, because as we are able to handle also hybrid applications, we were also having some issues when having more than one OpenMP thread, and we will solve that also.
Cool. Let's see if we have any other question. Not so.
I dropped one.
Hello, thank you, Connor.
Did you see it there? Or is it no?
Hello, we are listening.
Yeah. Okay. Well, here, I'll just say it out loud. So I say, great talk. Have you or do you plan to perform any qualitative case studies examining how TALP has led to new and interesting conclusions for users?
Yeah, so I was encouraging our support department at BSc and different colleagues also that are application developers and so to test it, to try it really in production runs. So the preliminary results, which are not into a high number of MPI cores because I just showed results for 700 MPI processes, but we wanted I wanted to test it in like thousands of MPI processes to really see this. But I have that feeling already because I have seen that when analyzing applications. So you analyze applications for developers and they really don't know what they are running. And they are running in thousands of cores and they just get a 50% efficiency. So that's where the idea of this tool came from, just to give them an idea of what they are running in case they need to rethink or analyze, because I cannot be there analyzing every single run for them.
Thank you.
Yeah, thank you. Does anyone have any question? You can unmute to ask if you want to. Just let us know in the chat so we can unmute you. Okay, so I have. Hello, Regina.
Hi. Wait a second, it's looping from my side.
Okay.
Yeah, I don't know, it's weird.
Did you unmute in Hoover? Because that's what caused problems for me. You have to unmute.
Oh, okay.
The Skype, yeah.
Yep. Okay. So I'm using X-ray and basic analysis, and also, so when I read about TALP, I also have, and hearing this presentation, I have questions. Since you are comparing the result between like TALP and basic analysis, what other things that that only can be done inside TALP but not in basic analysis? Because if you are comparing between these two with this result, for me it feels like it's actually kind of doing the same things as basic analysis. Can you please explain a little bit about that?
Yeah, so I'm sorry, Radhita, but I think the question is the other way around. So TALP is not doing anything else than it's doing Extrae. It's doing less, but in a very light way, so that you can get metrics for very large runs with adding very few overhead. So the idea is just my idea for this tool was something that almost every simulation can add, or every run in an HPC machine can add. And at the end, the user would see which efficiency their run got. So that it's something very, very light so that they can get a very fast and easy idea of how it's performing. And it's the other way around. It offers much less than the basic analysis, because you that are familiar with the metrics, and I realized that it's something I forgot to say in the presentation, what is hearing you again, it's that we are not able to compute any of the compute efficiency metrics, because for that you need the hardware counters, and adding hardware counters adds overhead, and we are not able to separate between serialization and transfer, because you need the simulation. So we offer less metrics, but I think that those few metrics can be very useful for average users. So the idea of TALP is like that, offering less, but being able to be used for everything.
Okay,
sorry that I didn't answer your question. I just turn it.
It's okay. I think like a lot of people will be like familiar with X-ray, but not with basic analysis. But since I'm using those two, and also like seeing this presentation, yeah, that was like what I have in mind, because yeah, okay, that's a good one. Have you made any comparison, like runtime comparison, like total time needed, like to run X-ray and basic analysis compared to when you're using TALP, something like that?
No, because with TALP you don't need any additional time at the end of the simulation. So you get everything at the finalization, you get the print, and that's it. So that all this extra time analyzing and going through basic analysis is not needed. But because you have much less information, we don't have all the timeline and all that. We just have the metrics. So the thing that we can have in TALP that it's not in basic analysis is the thing that we can mark regions. So if you know your code, you can say, okay, I want to get the metrics for region A and region B, so that you can get this information at the end separated, and it can give more information to the developers. And then the advanced version that I was saying, that it's with the API, where the application can get the metrics during the execution and try to adjust itself.
Thank you.
Thank you.
Thank you, Radita. And it brought me to another question, actually. The comparison with the basic analysis, the data used to that, you traced the whole execution or only the MPI calls?
With the basic analysis, I traced the whole execution. So, well, the MPI calls and the hardware counters.
Yeah. So maybe like tracing only the MPI calls, you can do more comparisons because there was a limit, right? Because it was generating huge amount of data.
Yeah, that's true. Maybe it would be fair to compare just with tracing MPI calls.
Yeah. Okay, Connor just dropped a message there. I appreciate how TALP is avoiding bloat by maintaining its focus. Yeah. Okay, since we don't have any other question and we are out of time, thank you very much, Marta, and we will move on to our next presentation.
Thank you to you.
So our next presentation, it's predicting how convolutional neural networks training time changes on various mini-batch sizes by considering convolutional algorithms and non-GPU time. It is a work by Peter Bresgalf, Toshioki Maeda, and Yotaro Shigeto, all from the Chiba Institute of Technology. So let's watch their presentation.
Hello, my name is Peter Bresgalf. I'm a chief research scientist at the State Laboratory of Chiba Institute of Technology in Japan. Thank you for your interest in our research paper presentation. Here is the title and the authors of our paper. The broad topic of this paper is the training time of convolutional neural networks, CNNs. Before getting into the main point of our work, I'll explain what typical CNN training is. First of all, CNN training is a simple repetition of processing the training dataset called epoch. More specifically, each epoch first splits the training dataset into smaller subsets called mini-batches, according to the specified mini-batch size parameter. Then for each mini-batch, we perform training iteration. More specifically, we first feed the mini-batch samples to the CNN. Then we calculate prediction errors by comparing the CNN output predictions to the desired results and then update the weights in the CNN by backpropagating the prediction errors. Changing the mini-batch size changes both the time of one iteration and the time of one epoch significantly. Though at first glance it may seem easy to predict how CNN time changes with the mini-batch size, it is very difficult because there exist two challenges. The first challenge is that a small variation in mini-batch size may cause abrupt changes in training time. It is difficult to predict these abrupt changes because they are caused by underlying low-level libraries. The second challenge is that for small mini-batch sizes, CNN training time grows sharply as mini-batch size decreases. We investigated this behavior and found that it is caused by non-GPU operations. Let us take a look at how the epoch time of sample CNN changes with the mini-batch size. Epoch time is the time to use all training samples exactly one time for training. On these figures we can see the epoch time of the change of EGG16 model for a range of mini-batch sizes on 3 GPU types. We can see there are places where epoch time drops or increases abruptly with a minor change of the mini-batch size. Such abrupt changes are caused by convolutional layers. Convolution operations are executed using a highly optimized library cuDNN, which selects different convolution algorithms for different convolution configurations. Convolution algorithms differ by execution time. Thus, a change in the algorithm may result in a significant change in execution time. Predicting these changes is a challenging task because cuDNN is a black box library. We could also see on the figures that epoch time grows sharply as the mini-batch size approaches 0. It grows faster than the reciprocal function, as would be the case with a linear correlation between the iteration time and the mini-batch size. Our experiments suggest that such growth is caused by non-GPU time, the time of training operations performed outside of the GPU. To demonstrate this, we performed training of the chain of EGG16 model with a Cypher dataset on a machine with NVIDIA V100 GPU. We ran training on a large number of mini-batch sizes and logged the epoch time. We also recorded the time of all operations performed on the GPU using NVIDIA's InVProf tool. We can see the gap between the epoch time and the GPU time, which grows larger towards smaller mini-batch sizes. This gap indicates that training time is affected by operations running outside of the GPU. To the best of our knowledge, none of the previous works considers this kind of non-GPU operations. Now I shall briefly introduce our approach to predicting CNN training time. Our approach considers non-GPU operations and abrupt changes in the CNN training time. We model CNN training time as a composition of the following components: time of convolutional and dense layers, time of other layers and GPU operations not associated with any layer, and time of operations performed outside of a GPU or non-GPU operations. The time of convolutional and dense layers is hard to predict because they are using a black box library cuDNN and may have abrupt changes. However, accurate prediction of convolutional layers time is very important because convolutional layers take most of the CNN training time. Our solution is to benchmark convolutional and dense layers with a proxy application. Then we aggregate times of individual layers according to the target CNN architecture. Please refer to our paper for further details. To benchmark convolutional and dense layers, we measure one iteration time of each layer modeled with the proxy application. As the proxy application, we use a versatile benchmarking tool called DNNMark. Benchmarking a layer only takes a few seconds for each combination of mini-batch size and GPU type. Benchmarking individual layers can be much faster than measuring the time of the whole CNN. Moreover, unlike measured CNN time, the time of an individual layer is reusable. It can be used for any target CNN architecture that includes the same layer configuration. By benchmarking convolutional and dense layers, we obtain in a reasonable amount of time reliable estimation that can be used for accurate prediction of CNN training time. The next component of CNN training time is the time of other layers and GPU operations. We model their total time per one iteration as a linear function of the mini-batch size. To estimate the iteration time of other layers and GPU operations on large mini-batch sizes, we use linear regression. To fit the linear regression, we measure target CNN epoch time on two mini-batch sizes. The first mini-batch size is the largest one, and another is the smallest one where GPU time is expected to be greater than non-GPU time. This figure illustrates our approach. On the top plot, we can see the iteration of the target CNN chain of GG16 model on a V100 GPU, the blue line. We can also see the aggregated time of convolutional and dense layers benchmarked with the proxy application, and the difference delta between the target CNN time and the time of convolutional and dense layers. We consider this delta to be the time of other layers and GPU operations, but only on large mini-batch sizes, where GPU time is larger than non-GPU time, on mini-batch sizes from 170 to 500 in this example. The lower plot shows the delta and our approximation with a linear function. To find this linear function, we use the target CNN epoch time on mini-batch sizes 170 and 500. The last component of CNN training time is the time of non-GPU operations. We model their time per iteration as a constant. To find this constant, we use the target CNN iteration time on the smallest mini-batch size. In the figure, our estimation of non-GPU time is shown as the dotted horizontal line on the upper plot. To summarize, we predict the target CNN epoch time from the epoch times of convolutional and dense layers, other layers and GPU operations, and non-GPU operations using this formula. Because GPU and non-GPU operations run simultaneously, we model CNN training epoch time as the maximum of the epoch times of GPU and non-GPU operations, where GPU time is the sum of the times of convolutional, dense and other layers and of GPU operations not associated with any layer. Epoch time value can be found from iteration time using this formula. To evaluate our predictions, we use mean absolute error and mean absolute percentage error on unseen mini-batch sizes. For evaluation experiments, we use 6 GPU types and 6 target CNNs. We use 50,000 images in the training dataset. Overall, evaluation results show that our approach can give an accurate estimation of CNN training epoch time over a wide range of mini-batch sizes for different GPU types, including cases with abrupt changes. The mean percentage error of all experiments is only 1.38%. The largest experiment error is 5.01%, and the error exceeds 3% in only 2 experiments. For some experiments, we provide detailed plots in Figure 5 of our paper. Here is one such plot, which shows the target CNN epoch time and our predictions, along with absolute and percentage error for each mini-batch size. GPU time predictions are accurate for most experiments. We observed the largest error in the experiment with the PyTorch 36 model on P100 GPU. However, please note that this is still less than the observed target CNN epoch time variability. In general, non-GPU time predictions have higher errors than GPU time predictions, and we are working on improving our predictions for non-GPU time. Here is the summary of how our approach is different from most similar prior works. Prior works build one prediction model for all possible CNN configurations, while we build individual models for each target CNN, with only one variable parameter to achieve high prediction accuracy. Prior works evaluate predictions on one or several mini-batch sizes, while we evaluate predictions on a wide range of densely sampled mini-batch sizes to address the impact of non-GPU operations and abrupt changes. Prior works predict the time of individual layers and have issues with the time of operations not associated with any layer, while we predict epoch time of the target CNN. Prior works do not consider non-GPU time while we do. Prior works predict the time of convolutional and dense layers, while we benchmark their time, which allows us to accurately predict abrupt changes in the target CNN training time. Here are the conclusions. CNN training time shows extreme growth towards the smallest mini-batch size, which is caused by non-GPU operations, and may have abrupt changes caused by convolution algorithms. We proposed a performance model that considers non-GPU operations and convolution algorithms and consists of 3 components. Time of convolutional dense layers. We use a proxy application to estimate the time of each layer. This enables us to predict the abrupt changes. Time of other layers and GPU operations, and time of non-GPU operations. We evaluated our model predictions on unseen mini-batch sizes for 6 GPU types and 6 target CNNs. The results show that our model could provide high accuracy with mean absolute percentage error of 1.38%. Here are the tasks for our future work. We could not reflect all reviews' comments in the paper due to the space limitation. Thus, we provide some additional information here. What significant use cases could there be for this research? The big goal of this research is to achieve the most time and cost-effective CNN training. In this work, we focused on 2 factors that have a significant impact on CNN training time: GPU type and the mini-batch size. Training time estimations for a wide range of mini-batch sizes on each GPU type would enable ML practitioners to select the optimal combination to minimize time and cost to train a particular CNN. Why the mini-batch size? We started with the mini-batch size because this training parameter has a significant impact on training time and can be easily adjusted before CNN training. In the future, we may consider other training parameters as well. What are the assumptions of this work? We always assume that the ML framework has exclusive access to computational resources, and no other tasks are interfering with CNN training. Will our method work for smaller dataset sizes? We use the dataset size of 50,000 as in the Cypher dataset in evaluation experiments. However, we believe similar low percentage errors would be achieved for predictions with other dataset sizes. That is because, for all three components that we use to model CNN training time, namely convolutional and dense layers, other GPU operations and non-GPU operations, we estimate their time per one iteration, and per iteration time does not depend on the dataset size. Related works. There are many works on performance analysis and prediction for GPU applications. There are also many works that consider performance analysis of deep neural networks. However, in this work we picked up only the most closely related works that cover prediction of CNN training time of one GPU. That concludes my presentation. Thank you for your attention. Hello.
Thank you, Peter. Are you there?
Hello?
Hello.
Can you hear me?
Yes, it's good. Thank you.
Okay. Good.
So thank you for your presentation. I really like your work. I think it's very useful for people, right? Like remodeling their scientific applications using benefiting from deep learning, right? Let's see if we have question. We have a thank you. You have a question here from Connor. So do you think this methodology can be applied to modeling performance changes with other variables besides mini batches, like the number of available cores on the GPU or other hardware configurations?
I see. In our method, we do not consider directly number of GPU cores or other hardware parameters yet. Maybe we will have to think about it in the future. So to be able to apply our method to some new configuration or new GPU, we have to benchmark convolutional and dense layers on this GPU. So that's it. So in this sense, it can be applied to any configuration, I think.
Thank you.
Did I answer your question?
Connor?
Yeah.
If you want to.
Yeah, you did.
Okay.
Thank you, Peter.
Thank you. Thank you for your question.
Also related with the parameters configuration, Peter, I saw in the end of the presentation you plan to vary other training parameters. What other training parameters are you considering?
We're not yet considering any, but there are maybe like learning rate. I don't know, maybe some works consider different kind of optimizers like SGD or ADAM, and with momentum or without momentum, etc. So I meaning parameters like this we may consider in future.
Yeah, good. And are you planning to extend your work for multi-GPUs environment?
Not yet, because it greatly makes it more complex, much more complex than one GPU. And on the other hand, if you have good, you can predict time for one GPU. There are other works that apply predictions for multi-GPU environments. So maybe there could be a combination of two methods.
I see. Yes, and using multi-GPUs will probably increase the parameters you can vary to.
Yes,
like
yes.
Number of mini batches, etc. Okay. Oh, we have a new question here
Mhm.
from Redida. I see that the test is using PyTorch. Do you expect that this model will also work for other CNN libraries?
Yes, we also tested with Chainer, but it's not used anymore. I think not used now. But we also plan to take a look at the TensorFlow. But our approach will work for any, I think, framework which uses cuDNN underneath, because cuDNN is an important part of our methodology. So yes, I think other libraries could be used also.
Mm-hmm. Let's see. We still have time if someone wants to text another question. In the meantime, I will ask one. Like we saw that the non-GPU time impacts the prediction, right? And I was wondering did you monitor the environment, the non-GPU environment, and to see if there was any other interferences of other programs running or other hardware, like network connection or something like that? And also if you monitor the GPU usage as well, because I saw like that you use P100 and V100 GPUs. So they have different functionalities like automatic mixed precision at the Volta ones, and also the tensor cores. So did you control also the environments that you were doing the experiments?
Do you mean hardware environments or
Hardware.
as for hardware?
Yeah.
For V100, we used Amazon cloud instances. So they this kind of environment. And for P100, we used Google Compute Platform. And we also tested on a supercomputer with P100 GPUs, but we have similar results. And and for monitoring non-GPU or CPU side, we didn't have any other programs running on the same machine, so there were no inference in this sense. And for monitoring, we didn't monitor during the execution, but we used profiling and tracing tools to understand how the framework uses hardware and what are the bottlenecks, what impacts the performance. So we use mainly NVIDIA Insight systems, profile tracer, and some other software also, profiling tools. And yes.
Okay, thank you.
Did I answer your question?
Yes, pretty much. Yes, thank you.
Thank you.
And we have another question here from Ana Lucia Varbanesco. Any thought on how to tackle distributed models on top of PyTorch, like, for example, Horovod?
No, we're not looking at the multi-node training yet. But because one reason is because there are so many different approaches to parallelizing training, like even sorry. So many approaches to parallelizing training. So, like we talked before, the complexity increases multifold. So we're not looking at that yet.
Thank you. Thank you, Anna, for the question too. Does anyone have another question? Okay. If you have another question, you can put on the Kuva or here in the chat, so Peter can answer later as well during the remainder of the workshop. So, okay, thank you very much, Peter, for the presentation. We will move on with our next paper presentation.
Thank you very much.
Thank you. So the next paper is entitled On the Exploration and Optimization of High-Dimensional Architecture Design Space. This is a work from by Vincent Bott, Fariz Husenli, Martin Schreber, Karsten Trinities, and Martin Schutz, all from the Technical University of Munich. So let's watch it.
I guess I got to reload for some reason.
Hi, my name is Vincent Bodi, and I'd like to give you a warm welcome to my presentation on the exploration and optimization of high-dimensional architectural design spaces. I'm from the Technical University of Munich, and this is a joint work between Fariz Husenli, Martin Schreiber, Karsten Trinitis, Martin Schultz, and myself. Now, we've been through several decades of high-performance computing, and still we're chasing the holy grail of optimal performance. While for some parties, the focus has shifted away from raw performance towards other goals, such as, for example, energy performance, we have not yet arrived in a post-scarcity era of compute power. This means that everybody is still trying to optimize for maximum output from their resources. Now, in a typical scientific setup, we have three parties that are all working towards a common goal of achieving performance. We have the application developers, which are scientists that want to conduct research and solve the big problems of humanity. To satisfy their computing needs, they turn to the computing center operators, which provide them access to the hardware that they need. The operators want to ensure that they are delivering the maximum output they possibly can from their budget. And one important step towards achieving this goal is acquiring the right hardware. To do this, the operators consult hardware vendors. The vendors, of course, want to sell their hardware effectively. Therefore, they want their hardware to achieve well in metrics such as performance, cost performance, or energy performance. Now, to achieve the best possible performance, we need to have hardware and software tuned to coexist. You can see that while all of our stakeholders want to achieve performance, none of them have the knowledge to achieve it by themselves. This is because the knowledge of the software lies with the application developers, while the knowledge of the hardware lies with the hardware vendors. The operators are usually the intermediary, with a bit of knowledge in both domains. However, they tend to lack the in-depth understanding that the other parties have in their domains. To be able to best serve their goals, each party needs to anticipate and account for other parties' needs. Since each stakeholder is usually not an expert in the other domains, we need increased collaboration to align vision and action. This is becoming all the more important because the heterogeneity in high-performance computing is on the rise again, increasing the reward of making the right decisions, but increasing the penalty of making the wrong ones. So your question might be, what can we do to aid the co-design process? Well, we can provide tooling. Tooling to help application developers, computing center operators, and hardware vendors collaborate. In this talk, we present HOT, the high-dimensional exploration and optimization tool. It is a tool that allows our co-designers to visualize application performance on a variety of accelerator hardware configurations. To achieve this, it uses a performance modeler to create runtime predictions for accelerator hardware. HOT currently uses Intel Advisor to achieve this, but HOT is largely independent of the performance modeler used. This is because all HOT needs from the performance modeler is a runtime prediction for a given hardware configuration. Now, once the performance data is loaded into our tool, the user can then explore the hardware configurations that can be modeled. Because in our case, there are over 8,000 different hardware combinations that we can test in Offload Advisor, we use an interactive visualization approach to allow the user to understand the performance constraints. Finally, HOT also helps the user optimize their hardware parameters. It allows us to specify a cost function that takes into account the different hardware parameters that is then used to achieve a target speedup using the most optimal hardware. More on that in a couple of minutes. Now, recently, Intel has released a tool called the Intel Offload Advisor. Offload Advisor is a tool that creates predictions for GPU runtime based off of CPU-targeted code. It does this in 3 steps. So the first step, it collects metrics on the application running on the CPU. In the second step, it analyzes these metrics that it collected and creates a model of how the application will run on the GPU. Finally, the third step, we can see the output of Intel Offload Advisor, the advisor report, in a browser. This is the so-called output step. Let's see what this looks like in a sample application. Here, we have a simple Intel Offload Advisor report. We collected this data from the benchmark application Lulesh, which is a Schlock hydrodynamics code written in C++ and parallelized using MPI and OpenMP. You can see that Offload Advisor gives us our measured CPU time as well as our predicted CPU plus GPU accelerated runtime. We get a speed up of a little bit less than 2, and we have a fraction of accelerated code of approximately 58%. Offload Advisor also shows us our individual compute kernels on the bottom left and categorizes them by top offloaded kernels, which are the ones that are moved to the GPU, and the non-offloaded kernels on the right that remain on the CPU because they execute faster on the CPU. Here in the top right, we can see that it's possible to change the hardware parameters as well. What you need to do in order to create new runtime predictions using Intel Offload Advisor is set the parameters to the desired values in the interface, like so, then download the newly generated configuration file, rerun the analysis phase, and finally take a look at the newly generated Offload Advisor report. This is what our tool automates. It can show you all the possible hardware configurations supported by our modeler. Now our modeler has support for 5 different parameters. For consistency, we're using the same nomenclature that Intel Offload Advisor uses. We have the absolute frequency in gigahertz, which determines the clock rate of our GPU. We have the number of execution units relative to our reference GPU model, as well as the relative L3 cache bandwidth and memory bandwidth. The cache and memory bandwidth can be set all the way up to infinity, at which point the bandwidth can no longer bottleneck the computation. Finally, we have a binary setting that determines whether the accelerator is located on board or whether it is attached via PCIe. Now, each parameter has a number of discrete values that it can be set to within a predefined range. In total, that means that there are 8,624 different valid hardware combinations that we can test and examine. Now, because there are so many different possible combinations of hardware parameters that we can try with our modeler, we need some sort of way to efficiently analyze and visualize what GPU combination is best. To achieve this, we use what we call pivot visualization. Now, pivot visualization only visualizes a part of the high-dimensional space at once, but it compensates for this by being interactive. Here, we have an example in 2 dimensions for the sake of explanation, but this approach also generalizes to a higher number of dimensions. We have this large 2-dimensional grid here, which covers all the possible combinations. However, we only visualize a single dimension each along each axis, which is determined by where our current pivot is. So our current pivot is marked here in red. We visualize the possible changes along this dimension, in this case the first dimension, in blue. On the second dimension, we have the same thing. Red still represents our pivot point, and blue represents all the possible other options along this axis going away from our pivot point. This means that rather than visualizing the entire space at once, which is a little bit hard once we get a lot of dimensions, we just visualize a portion of the space. We prefer this method over other existing methods for high-dimensional visualization, such as RADVIS, parallel coordinates, or TSNE, because it preserves the visibility of individual input dimensions, and because we are mostly interested in local trends rather than viewing the entire space at once. Now, what we can do in order to explore this high-dimensional space is we can move our pivot by clicking on one of the graphs. Say we want to increase our performance. We can see that we can do that by changing our pivot, so we increase the dimension 1 parameter. This moves our pivot to the new point we can see on the right. Subsequently, all the graphs are updated to reflect the new performance data. Our second dimension graph now shows us a new trend according to the new values along the second dimension. Let me show you how this works in the actual tool. This is the interface of the demo version of HOT. We have made it available to the public online. In the demo version, we also provide performance data that we collected, besides the possibility for users to collect their own performance data. Let us take a look at it now. We provide data for 4 benchmarks: Lulesh, Stream, Gadget, and 2mm matrix multiplication. Stream is a benchmark that we know is memory bandwidth bound, so let us take a look at that first. We have a graph for each hardware parameter using the same naming convention that the modeler uses. And the red dot on each of the charts represents the current value of the hardware parameter, with the initial configuration representing our actual physical GPU. The other possible values of each hardware parameter and the corresponding performance are distributed along the chart's x-axis. Okay, so we can see that using our current GPU, the relative runtime savings that we can achieve, where of course higher is better, are virtually non-existent. It's also easy to see that no matter what we set our GPU frequency, number of execution units, or L3 cache bandwidth to, there will be no significant speed up of our code. Changing memory bandwidth is the only parameter here that can get us a significant gain from our current configuration. So let's go ahead and change that one. Let's say that we can pay for a memory bandwidth of 96 kilobytes per second. Now we can see that our runtime savings have improved to 60%, which is equivalent to 2.5x speed up. Still, we see that the only thing that can improve our performance further is memory bandwidth. So let's try something different. Let us say that our boss gave us no restrictions to our spendings, and so we decide to buy a GPU with unlimited memory bandwidth. Well, we are now over 90% runtime savings, or a speed up of approximately 10x. This is not particularly exciting for a GPU with unlimited memory bandwidth. So we can now see that other parameters bottleneck our computation. At this point, it can be useful to switch from relative runtime savings, which we use as the default because the metric is linear with respect to program runtime, to speed up, which is more useful for viewing high acceleration factors. We can see that in order to get past the 10x speed up barrier, we can either increase our GPU frequency or our L3 bandwidth.
Connor, are you there?
Let me.
Okay, thank you.
This further improves our runtime.
There we go.
We can keep doing this until we max out all the parameters, which places us at a speed up of over 200 compared to our CPU runtime. This analysis allows us to easily examine what sort of accelerator hardware is suitable for our system. Another thing we can do with HOT is compare the performance between multiple benchmarks. Say we want a GPU that works well for both the stream and matrix multiplication benchmarks. By selecting both measurements runs, we can compare their performance directly, and this allows us to tune our hardware parameters for multiple benchmarks at the same time. Another thing we can do is we can compare the performance of benchmark changes when we change the benchmark's input data. This works the same way as comparing different benchmarks works by just selecting multiple different measurement runs. Here we can see that the expected speed up for Lulesh on different dataset sizes diverges a little bit. This change alone can already affect the predictions by up to 10%. Furthermore, we can repeat the exact same measurement several times and load it into HOT. This allows us to examine how stable the output of a modeling tool is. Here we have 4 runs of Ludash on the same configuration, and we can see that while there is some variance, the overall performance trend is clearly visible in all of these experiments, which boosts our confidence in our modeling tool. HOT also currently includes an optimizer for hardware cost. It assumes that the relevant hardware costs increase linearly with respect to each of the hardware parameters. In the problem formulation here, we have a vector of parameter values x and a vector of cost coefficients c. We try to minimize the total cost, which is the product of these vectors. We need to ensure that our performance predictions f of x is greater than or equal to our target runtime savings goal, and we need to constrain x into the set of valid parameter combinations p. Now, obviously, this is a little bit of a simplification of the real-life costs because increasing frequency, for example, definitely has higher order costs because of the power wall. However, we believe that it's still useful to have a linear model as an estimate, especially because it is difficult to determine the manufacturing costs of each of these parameters individually. As far as we are aware, there are no publications to date that divide the manufacturing costs of GPU down into the relevant hardware parameters. So currently we have to use imaginary values. Because the number of possible combinations is very manageable, and our performance prediction f of x is easy to evaluate, because we have pre-computed all the different possible values, we can forego optimization algorithms such as the simplex algorithm for a simple brute force approach. Since we exhaustively analyze all the possible configurations, we can then plot the configurations on a performance versus cost scatter plot to find promising configurations. We specify the minimum relative runtime savings that we want to achieve, let's say, for example, 35%, and all the viable hardware combinations will lie to the right of this half plane. The most optimal solution is the one with the lowest cost that satisfies this constraint. This means that the best configurations lie towards the bottom right, with high performance but low cost. It is possible to observe here that the higher the target runtime savings are, the more expensive the optimal hardware configuration becomes, which is kind of what we expect. We can also see that the cost tends to jump higher at certain performance thresholds, and this is where we need to increase an expensive parameter in order to be able to achieve the required performance, which in turn, because the parameter is a little bit expensive to increase, also incurs a larger manufacturing cost. So let me show you how we can use this optimization interface in HOT itself. So this is the optimization view. In this view, we can set the target for the minimum runtime savings that we want to achieve. Let's say that we want to cut down the runtime by at least 30%. We can see that the cheapest configuration sets the frequency parameter to its second lowest value, while keeping all the other parameters at their minimum. This incurs a total cost of 23.40 and generates runtime savings of 33%. If the frequency becomes more expensive to manufacture, the total cost will rise until eventually it's cheaper to raise the L3 cache bandwidth rather than having the frequency be higher. We now have a GPU with a cost of 25 that saves on 32% of the runtime. Let's say we want even more performance. We can keep raising the minimum runtime savings and watch how the parameters are automatically adjusted for the performance requirements. Eventually, we arrive at the best configurations that our modeler supports. If we raise the runtime savings further, the optimization problem becomes infeasible. Going back to the best performing configuration, we can load this configuration back into the overview and continue analyzing our application.
Sorry, we had to stream this one. We couldn't download it, but gonna reload the page and just scrub over to 1860. So oh no.
So to summarize, what did we take a look at today? For one, we took a look at the importance of hardware and software co-design and why it's becoming increasingly important that application developers, computing center operators, and hardware vendors collaborate in an effort to push performance barrier even higher. We took a look at the tool Intel Offload Advisor, which allows us to predict GPU runtimes based off of CPU codes. We use that to create a range of predictions for a visualization tool, HOT, the high-dimensional exploration and optimization tool. And finally, we optimized some hardware parameters and found the best way to reach a certain threshold of performance. Now, there are some improvements that still can be made to HOT. For one, support for different hardware modelers could allow us to compare predictions for more diverse hardware targets, or even across multiple different modelers. There's also still lots of potential for improving optimization component, including the potential for a more advanced cost model than the linear one we have right now. Finally, we want to examine more benchmarks to extract interesting performance data from them. We are currently also looking for new applications for this visualization technique, for conducting parameter studies, and would appreciate your input. A demo version of HOT, including sample data we collected on one of our machines, is available online right now under the link displayed on screen. That's it from my side. Thank you for listening. These are my contact details, and now I'm open for questions.
Okay, thank you very much, Vincent. Are you there?
Thank you. Yeah, I'm here.
Thank you. And sorry for the interruptions during the presentation.
No problem.
I really encourage you who are attending to rewatch the presentation later. It's in the proceedings page. So we have a question here from Connor. Is there a reason why I would want less than maximum optimal cost savings?
That's a good question. So right now, what we do with HOT is we kind of look at the trade-off between cost and performance. So in the tool right now, how it works is that we specify a performance that we want, and it'll give you the optimum configuration to reach the lowest cost possible. There's, of course, other things that you can consider. So right now, the Intel Offload Advisor doesn't yet model power consumption, but power consumption might also be another parameter that you might want to take a look at. All these things can be considered. But in general, what we're trying to do right now is just finding the easiest way or the cheapest way to build an accelerator with a specified dedicated runtime savings or speed up, whichever metric you prefer.
Thank you.
Thank you. Does anyone have another question? You can drop here in the Zoom chat or at the Hova platform. We are monitoring both. In the meantime, I'll ask one. So do you plan to extend HOT for non-Intel platforms? What will be an equivalent data such as the one obtained in the Intel Offload Advisor?
Okay, so the first part of the question was, do we plan to extend it past the Intel platform?
To non-Intel platforms.
Yeah, so right now the future plans are not exactly clear. The reason that we're using Intel right now is that it's interesting to our computing center. I'm not exactly certain what simulators exist right now for the other platforms already, but it is something that we have on our roadmap eventually, where we want to take a look whether other hardware vendors could also be, we can also use the tools from other hardware vendors to collect similar or the same data.
Mm-hmm.
And it will also, of course, be interesting to see whether the same configurations or similar configurations kind of lead to different results on different vendor tools. And sorry, I didn't get the second part of the question.
Yeah, so using non-Intel tools, you will depend on other tools, not as the Intel Offload Advisor. So where would you obtain that data?
That's a good question. So right now, I'm not exactly sure what else exists. That's something that we would have to take a look at.
Mm-hmm. Okay, good. Thank you. Let's see. No questions yet. And did you evaluate how for other benchmarks other than Lulish?
Yes, we did evaluate for other benchmarks than Lulish. So I think in the demo data that we included in the web demo, I think we put in 4 benchmarks, if I remember correctly. We did try it on a bunch of other benchmarks. We did not always have so much success in collecting the data properly. So to us, even with the help of Intel, and we had quite a bit of help from Intel on this project, it was a little bit hard to collect good data with the offload advisor. So to me, it's still quite a bit of a black box, and it's a little bit hard to kind of, get proper data. It's a little bit time intensive, but we kind of included the most interesting results for us.
Yeah, I see, but you are doing a great job in the platform. Like, it's really cool and useful. We have a question here from Redida. I also have the same question. Can we do the hot analysis without Intel? Thanks for asking, Anna. Yeah, I don't know if you want to add anything else about that.
No, yeah. So this was actually something that already came up quite a bit, is why it's so Intel centric. So maybe that's something that we just need to take a look at more.
Yeah, I see. Okay. See if have any other questions. Still have some time. And you asked about suggestions at the end of your presentation. I have a couple. So
okay.
Like I like it that you can plot the repetitions data from the same experiment but different repetitions. It will be nice, like, to see the mean of the measures for all of them, so we can directly get this comparison result from using the platform. And also it will be nice to download the plots and also the configuration you are using, like download the plot individually or not, if the person wants to report or something like that.
Okay, thanks. That's already useful. I can take a look at those things.
Okay. Oh, we have another question from Redida. How confident are you with the numbers provided by the Intel tools? Is there a way to do sanity check with proprietary tools that you can share?
Okay, yeah, this is a good question. So the short answer is I'm not extremely confident in the numbers that are provided by this tool. We did do a cross-check with actual hardware available to us. So actually running the same benchmarks on physical hardware. Let's say it's tricky to get the numbers on the simulation tool, emulation tool, to look like the numbers on the actual hardware GPU. So this is something that's still relatively new as far as I'm aware, and they're still working on making the models work nicely. But right now, I wouldn't say that I have full confidence in the modeling tool.
So thank you for the questions. If you have other questions, you can put in the chat here. We will be using the same Zoom session until the end of Permavost. So thank you very much, Vincent, for presenting and being here today.
Thank you for having me.
Thank you. So this concludes our paper presentation session. I would like to thank all the paper authors and presenters who were here for sharing their work with the Permavost workshop, and the audience works well assigned with the workshop proposal. And I think we could have good discussions about visualization analysis tools, and also visualization methodologies applied to different contexts brought with the papers we saw. So I would also like to thank the reviewers that brought fantastic and complete revisions and comments for all papers. That definitely brought value to the Permavost workshop. So thank you very much. We really appreciate that. And thanks everyone to attend this, who attended this session. And we'll be right back in around 15 minutes with the panel to discuss the future of performance analysis and engineering. So you can have time to grab some water, and you are invited to stay here and watch the panel. So thank you very much.
Perfect. Okay. So I believe that now is long enough that we're going to start our discussion panel, which is going to be on the subject of the future of performance analysis engineering. My name is Connor. I am one of the co-chairs of the Permavost workshop. And in this panel, we're going to have a team of 4 experts, in performance analysis, parallel computing, and distributed systems, discuss the future of performance analysis. Hopefully we'll glean some interesting insights about what is coming up. In particular, we want to place an emphasis on the growth of CPUs and cloud computing, how that might be changing the landscape of what we consider traditional performance analysis. And in addition to that, we're hoping to sort of discuss the limits of today's technology and what sort of barriers to progress are keeping us from getting into the next level. And I'm going to start off with just a little bit more context as to what this panel is. It's going to be a panel primarily with our experts here, but we would like others to participate by typing in your questions. Please engage in the conversation. Feel free to post in both the Slack chat or the questions chat on UVA. We'll be monitoring both of those. And yeah, I believe I'm going to start with just asking each one of my panelists to introduce themselves, if they'd be so willing. And let's start in the order of the pictures that I have here, if you guys can see that. So from left to right, let's begin with Olga. If she is there. I didn't lose her.
Hello, can you hear me?
Yes, there she is.
All right, so I am Olga Pierce. I am a computer scientist at Lawrence Livermore National Laboratory. So this is my, let's see, I've been there about, I've been there more than a decade, but in my current capacity, about 7 years. I did my PhD work in performance tools. And so that's one of my research interests. Other interests of mine are just, parallel algorithms, data structures, programming models, and everything related to optimization and modeling of performance.
Great, thank you, Olga. All right, now let's move over to Guido.
So hello, my name is Guido Juckeland. I'm working in Helmholtz-Zentrum Dresden-Rossendorf in Germany, which is, well, yeah, one of the large German research labs that we have of the Helmholtz Association. I'm heading the computational science department here for the last about 5.5 years. So with that, I've basically switched sides. So I've before I was also running HPC systems, making sure that users were happy, working a lot with hardware accelerators. Did my PhD on trace-based performance analysis for hardware accelerators. And now I'm more on the other side, working with scientists on getting their work done, which in a lot of cases also involves some performance studies and understanding why code isn't as fast or as efficient as it is. And especially when hardware accelerators come in, this opens up a whole new can of worms.
Awesome, thank you, Guido. And Max?
I'm Max Katz from NVIDIA. I'm a solutions architect, and the solutions architecture team is focused on technical support and being liaisons with our enterprise customers. And so I spend a lot of time working with developers and users, understanding NVIDIA's platform. And one role that I unintentionally carved out for myself in this role was the expert on our team on performance analysis and developer tools. And so I spend a lot of time working with scientists on understanding how to use performance tools, specifically in the context of GPU performance analysis.
Thank you, Max. And last but not least, Lucas.
Yeah, thanks, Connor. So I'm Lucas Schnorr. I'm from the Federal University of Rio Grande do Sul here in Brazil, south of Brazil. I'm associate professor, and I have been here since about 10 years already. And my PhD work was about performance analysis and trace visualization. So I have been in this field of trace visualization for quite a while already. And in the last years, I have started to look into the data science tools to do this type of work. So I'm going to talk about this perhaps in the upcoming discussion. So that's it. Thank you.
Awesome. Thank you guys for those introductions, and thank you once again significantly for being here for this panel. We appreciate it a lot. Now, let me start off with my first question I've got here. And these questions are definitely open for everyone, but I'm usually going to call out some people that it may be of particular interest to. And this first one, we were kind of thinking about Max and Olga on this one. And I'll just start off by reading. So, considering the scope of the Permavost workshop to unite performance analysis tools developers with a variety of experts in different fields, how can we make performance analysis tools more understandable by those experts in non-computing fields or with diverse HPC knowledge expertise? And I'll start with Max over here.
Yeah, thanks for the question. So application developers, when they start using performance analysis tools, are usually starting from their knowledge of their application and want to tie that into some knowledge of the platform that they're running on and how to improve the performance of their application on that platform. But the tools developers, who are often vendors or third-party groups, usually are starting with their knowledge of either their tool or more commonly the platform, and then attempting to build a tool on top of that knowledge. And so what you see is that in a lot of developer tools, that the focus is on collecting metrics and other counters that help you understand the nature of how the application ran on that platform. And then from there, they attempt to then, if we're lucky, turn that into knowledgeable or impactful outcomes, right? And so some amount of advice on what to do. But I think that really it's that advice that is the key thing that you have to start with, and then from there, turn it into ninja level knowledge if that's even necessary. And so, an outcome of this is that a lot of tools focus on giving you access to as many metrics as possible and other sorts of performance analysis, roll-up information. And that's great if you're a ninja developer on the platform. But the context of your question is, how do we make this more accessible to people who don't have ninja level understanding of whatever architecture that you're running on? And so I think that the key really is for the tools developers to put themselves in the mind of the user and ask the question, if I'm a user who doesn't yet understand the platform that I'm running on and I want to, how would I write the tool to make that possible? And this is a hard question, right? It's not an easy thing. If it was easy, I think people would do it. But I do think that the tools developers need to constantly be thinking of this question in this light. How do we develop the tools from the mindset of a user who isn't yet an expert on our platform? And for that, we really need, I think, the users to keep beating up on us, us developers of tools, and say, hey, this information didn't actually help me. I couldn't use this information to improve my application performance or understand the platform. Please make it more accessible. And I think the tools developers need to listen to that kind of request.
Olga, do you want to continue with that?
Yeah, sure. So I would add a few nuances to this. One, we actually have at Livermore, at least, we have large multidisciplinary teams. And so you may have subject experts, in computer science and subject experts in physics working together, because specifically for that reason, right? Because as a computer scientist, it's kind of difficult to expect me to understand physics on a PhD level, and vice versa, right? If you're wanting to have physicists understand computer science at a PhD level, that too is kind of a steep lift, right? So we have a human answer, if you will, to this question, where essentially we partner with each other to attempt to get at some of these questions. Secondly, there is a little bit of a separation of concerns oftentimes, and that is that a physicist may be writing a specific computation piece that they're deeply focusing on performance of a specific loop or specific function. And that's what they're concerned with at the moment. That's the algorithm they're writing. However, as you all probably know, in a simulation, there is a lot of code that goes in, in addition to that. And we oftentimes have computer scientists focus on those portions of the code because that is not a physics algorithm, right? That is really communication on the platform, things like that. So that's separation of concerns, and right now you kind of need different tools to get at those different concerns, which is another can of worms. And third, so Max is talking about a specific platform. What you may typically find is that applications have to live through many generations of platforms, and they have to execute on different platforms. So our applications run, on CPUs, on GPUs, getting ready to run on different types of architectures in the future. Had to run on Blue Jeans just a few years ago, right? Sometimes optimizing for a specific platform is actually going to kill your performance on another platform. So one of the thought processes that also happens in the background is that, will this optimization that I want to perform for this particular platform kill my performance somewhere else, right? And if that is the case, perhaps if you're not able to abstract it and make it so that you can have the best of both worlds on both platforms, you may have to forego some optimization because you have to be remain portable and so on.
That's it's really interesting. I'd like to actually expand a little bit on something that Max said when he was talking about listening to like customers and stakeholders. Kind of, do you think that there is enough channels for people to get their feedback back to the tool developers, or if we maybe need a better accessibility between the engineers and the users?
I'm glad you asked that, because I was thinking about that as I said it. And one thing that occurred to me is that, my job is basically to be that channel, or at least that's one aspect of my job, right? Is to be a computational scientist myself, and then listen to computational scientists and translate what they're saying into the language of our engineering team. And so that's part of why I exist at NVIDIA. And even if I do a good job at that, and I hope that I do, the impact of that is limited to the few customers that I have time in my day to spend, working with. I've worked with Olga and Livermore in the past, and hopefully I do a good job supporting them, but they're just one customer out of many, right? And the problem is, if you don't know me or an equivalent of me at a vendor, I honestly don't believe it's that easy for you to get your feedback to the tools developers, right? Usually the vendors, the tools developers have some sort of public feedback mechanism, but the reality is that if you don't already have a relationship with them or you're not already paying them, it's hard to get your concerns addressed. And I wish that I had a great answer for you on how to fix that. I don't think that I do, but I will say that To the extent that the tools developers can do anything about that, it's probably to invest more in making sure that you have people with a background in both the computational scientist and something of the computer science architecture to be a kind of bridge and support the users in giving them a feedback mechanism. And those people have to be trusted within their teams or their companies in order to provide that feedback. So it's not easy to develop such a person, but I think it's critical that you do that, because otherwise the tools developers pretty much only get feedback from internal users who are usually experts on, on the architecture. And so that makes it hard.
Yes, Olga, please.
So I think for this reason specifically, one of the first questions that we get for any tool is, how do I dump the raw data so I can look at it? Right, and it's like, oh, that's great, it's collected, it has a GUI, I don't understand the GUI, give me the data. And that's a tough one, right? And so you then see people wading through, well, first they are trying to get the data, then they're wading through this data, and then they're trying to make some sense of it. It is difficult. So, on one hand, if you don't have a user interface, it is hard to let the people see what you're collecting and what information you do have and what you're able to do with it. But on the other hand, there's so many platforms, there's so many tools. Sometimes at the end of the day, people are just wanting to say, I'm just going to write my own Python script to deal with this. Just give me the data.
All right. Thank you, Olga. Thank you, Max. So I'll move on to the next question. I'm looking over my shoulder here. I'm not seeing any new ones. So this one's kind of a statement than a question, and it's oriented more toward Lucas and Guido here. So I'm going to start off by explaining this thought process is that HPC is key for scientific advances, and its contributions come from like a wide variety of sources. We got stuff from industry, universities, and research laboratories. And within this like diverse ecosystem of HPC technologies, there's a wide variety of performance analysis tools and even methodologies, which are commonly used within each environment, sometimes or oftentimes to the exclusion of others. You'll use one, you won't use another. And many of these tools and methodologies serve the same purpose, but use different APIs, data formats, and user interfaces. And this diversity can pose a challenge for computer scientists worldwide to do robust and collaborative research. So our question on this is in two parts. One, do you agree with this statement? It's not necessarily a fact, and so I would like to hear your opinions on that. And then two, what barriers currently exist toward the adoption of a standardized set of tools for performance analysis, and can these barriers be overcome? And I see Lucas nodding there emphatically. I'll start with him.
Yeah, I can start. Thanks a lot, Connor, for the question. So before agreeing or disagreeing, let's say that having many performance analysis tools actually is I think it's a good thing for the community, because there are many different topics, and it depends a lot on the specific application code that we want to analyze performance. So I don't think that it is a challenge to choose the performance analysis. So for example, when we want to do tracing of a specific application, we want to have the most rich data from that behavior that when we run in the power computer. So choosing the application is a challenge in itself. So from that point of view, I think I have to agree that is definitely a challenge. But from the other point of view, this diverse set of tools, they usually have some way to export the data to a generic file format, such as CSV files or any other columnar based format that is faster to read. So in that sense, I think that's because I think that's a very good thing to have these different tools. But I speak of that because I'm a computer scientist, so it's easy to play with these different tools because they usually do the same basic things as far as from the trace point of view. But when we go to people that are just developing a tool, a computer, let's say a parallel application from physics or from biology, they usually have no idea of how to measure performance. And for that type of persons, it becomes very hard actually to understand what type of tool or methodology could be more useful for their application. So my final answer for this would have to, it depends on the people. So I would not say agree or disagree, it depends.
Gotcha. And you, Guido?
So having worked on performance tools myself, so vendor unspecific, so a research-based performance tools myself, I would agree that, you know, the multitude of APIs is somewhat troublesome. The benefit is that more and more programming models themselves actually recognize the value of a tools API, a profiling tool API, or a performance tool API. So with MPI, with PMPI, you have this forever. OpenMP now has OMPT. OpenACC has hooks where performance tools can get into. CUDA has CUPT. HIP or AMD HIP has something as well that works in some way. So the places are there so that actually the research-based tools, which are usually more interested in this, building those bridges between those various areas of concern. You know, I wouldn't expect Max to support profiling on AMD GPUs. I mean, it would be nice if we could use the NVIDIA tools on that platform as well, and actually also on CPUs, because they do some pretty cool stuff from application developers' point of view. But you know, it's not the expectation. So this is probably where researchers come in, and in the end, we also want to earn our PhDs or give PhDs to our various students where they can, you know, shine and do cool things. So to some extent, we have some standardized APIs which at least, you know, do similar things across different platforms. And the hard part, at least from a computer science point of view, is actually, you know, how equal is this similar? And, you know, as Max said in the very beginning, you know, what we do is we try to collect various metrics, and then we try to make sure that they actually mean the same thing if you measure on CPU A and hardware accelerator B. So that if you present them to an application developer, that basically means you screwed up on this line of code. You know, if this metric is high, for example. And that is actually a pretty tough computer science, you know, problem to get to that point. So also maybe as a follow-up to the previous question, so what I've seen most of the time is like this division of labor that Olga described. You basically have the computer scientists coming in with their tools that they know well, and then actually, you know, co-working with the application developers on looking into that application. Because also, as Lucas said, actually knowing what is the right tool for the question that I'm currently asking towards performance of my application is extremely tough. You know, am I just looking for a little magnifying glass to look a little bit closer, or do I need a full-blown microscope, or do I want to go the full electronic microscope thing, you know, electron thing, where I can, you know, look at every little, you know, clock tick all the way down to the CPU is a different question. Sometimes also a question that application developers either don't care in a lot of cases because it's good enough, the performance they're getting, or they simply also don't know, you know, what the right answer to that question is. You know, how much level of detail are they actually interested in to understand or to get that question answered?
Yeah, I mean, it's really interesting. And you touched on something there that I feel like may be problematic in the proliferation of these tools and stuff, which is the specifically from the academic side, but I mean, I'm sure it probably exists in industry too, that people like to build new things. They're interested in building new novel things. And I mean, maybe we have a proliferation of people who just want to build something new because it's fun, even if the functionality may be represented somewhere else. Yes, Max, please.
Yeah, I'm sympathetic to that point. That I do suspect that if I could put a slightly more positive spin on it, right? Vendors develop new tools also to accentuate the value of their platform, right? Not just necessarily to build something because they could, but because having something helps, you know, sell the value of the platform that you're trying to sell. And when I look at what it takes to take a CPU accelerated code, typically, and I'm sorry, a CPU based code that's, you know, perhaps been around for a while, and convert it to GPUs, this is typically a disruptive task, right? Most people who try it don't have codes that were already written in a way where it was easy to do, right? It took time and effort and understanding to do it. And I believe that there is some benefit to the fact that they can't just use their old tools to do that, because the old tools that they were using, if they were jury-rigged to make it possible to do GPU performance analysis, for example, they might mislead you into thinking that the way that you think about it is basically the same way that you think about CPUs. And I think that we have seen this shift in how you think about writing code over the last 5 or 10 years, where now massive levels of parallelism within like a shared memory approach is what you have to do to make your application work well, right? Regardless of specifically that it's GPUs, for example, most platforms are moving in that direction in high performance computing. And so that level of massive parallelism is important, and understanding like where your memory is super important. And these are things that you could have thought about a little bit less 10 or 15 years ago. And so if the tools had not evolved and changed radically to support that, they might have given the users you know, too much comfort in thinking that they didn't really have to change their application. And so I'm not necessarily, you know, providing apologia for the fact that our tools are different from the other vendors, but that there is like a silver lining in that, and that it forces you to shift your brain and think about this problem in a new way.
Olga, please.
Yeah, to just kind of pull on that thread just a tad more, I think what happened actually is as we were starting to think about the shift to the GPUs, we didn't have the code yet to use with the tools, and the tools weren't quite there yet. So actually the shift occurred in here, right? We had to rethink algorithmically, how are we thinking about this? Where's the extra parallelism going to come from? How do we enable that parallelism that these platforms are going to require, right? And so in some sense, it's actually the mental model that the application developers have of their code and of the parallelism of the platform is key to them being able to successfully you know, utilize those platforms. And so to me, that means that those tools that we're developing needs to be able to match the mental model, or, you know, essentially, you know, a developer comes in with a mental model, but the tool needs to supplement it with information that the developer can then plug into their mental model, right? And have it all make sense in their head. So that's the tool's job, right? Is to provide that information to validate the mental model, or to say, hey, you're missing something key over here. So that's an important piece. But yeah, largely performance analysis still largely happens in people's heads. It's it's an algorithmic process.
All right, well, I see that we did get a question from Radita here, so let me drop that in. She says, do you see the performance analysis tools will go more open source in the future? The black box nature of proprietary tools often reduces users' confidence on the metrics number integrity. That's her claim, at least, is the second part.
I think I can start answering that question. Today there are several groups in Europe and in the United States that develop some performance analysis tools I can cite ScoreP, for example, or the Extra E2 from DBSC, or even Tau from Oregon. All of them, they provide some sort of exporting the data. So there is, for example, the ScoreP is based on the open trace format version 2. So you can use the API to export that data for for a more open format. I mean, even more open, like let's say textual format, for example, in CSV files. And I think that type of effort is very good for the community because it allows the collaboration using different tools. So for example, if you want to use Scorpy for one task, go for it. And then I will be able to use the data anyway because I can export it to CSV file. Or if there is someone else that prefers to use other tool because it is more acquainted to that, for example, Tau, it can also export. So I can leverage these both tools to make it just one performance analysis of the application. So having these different views is quite positive. So I have a very positive view of these efforts of towards the open source because they allows a more collaborative research.
Thank you, Lucas. I wonder, Max, do you have a thought on that coming from NVIDIA, which I feel like that's a reference to NVIDIA, possibly.
No, it was continuing the previous discussion.
Just continuing. Okay, okay. No offense intended, of course.
I think that, you know, a company like NVIDIA is interested in innovating on what's possible in the field of accelerated computing. And we're not apologetic about that fact, right? We like the fact that we are coming up with new ways for developers to get every ounce of juice out of the platform. However, of course, we understand that there needs to be a place, and perhaps the majority of our developers need to come from a place of they're familiar with those open source tools and products, and they're not going to be computer science ninjas, right? And we expect that that's true for most of our developers. So we have to fight this tension between making our tools accessible for the majority who kind of want, you know, some level of universality in the tools that they use across platforms, and also supporting the Ninja developers who want to get everything possible out of the platform that we would provide. And so my sense of the trend has been that the community is mostly pushing pretty hard on vendors to support open source platforms. And I think you've seen, or I've seen in my 5 years at NVIDIA now, a lot of movement in that direction, both in the support of tools and compilers. And I think that trend is going to continue. And so I think we and other vendors will probably be forced to engage more in that ecosystem. And we're doing so happily, I think, right? I shouldn't use the word forced. We are engaging intentionally. But I don't think you'll see our vendor-specific tools go away, right? Because we want to support users who want to get everything possible out of the platform. And we have a lot of those users, right? We are not just HPC platform, right? We're also a high-end machine learning and AI platform, and we have users at places like Microsoft and Google and Facebook and other places who really do have quite a large number of computer science ninjas themselves and who do want to excel. And so I don't think that'll go away, but I do think that we and other vendors will probably have to engage more on open source tools and at least support those tools, if not make our own tools join that trend.
Oh, cool. Let's go, Guido.
No, I won't step in front of Olga. Please go ahead, Olga.
Okay, if you insist. I was just going to say there's room for both, right? So we definitely need the open source tools, and we definitely use them. But like Max was saying, when we really need to get to the nitty-gritty of performance on a specific platform, we pretty much have to go to the vendor-specific tools.
Yeah. So what I wanted to point out is that even more valuable from my point of view as an open source tool developer, former open source tool developer, unfortunately. So I still think of myself of, you know, messing with the code, which I haven't for a couple of years, is actually this open communication about open APIs, which gives open source tools access to the same level of information as the vendor specific tool. So, you know, should we want to build something to actually look extremely deeply into like an NVIDIA GPU or an, you know, AMD GPU or even an Intel GPU, for example, you know, this communication is happening now. And, you know, what application developers don't have to care about is that the tool developers on both sides, so the open source tool developers and the teams within the companies, are actually in a very engaging and lively discussion about those APIs to, you know, what to expose, what, you know, what's necessary. And you know, in a platform like or an API like CAPTI, where in the design I was also heavily involved in, is, you know, that was a multi-year process of people talking to one another, going through multiple rounds of, you know, draft APIs. And with this, basically, you know, open source tools can acquire the same level of information that the vendor tools can. And also, to picking up again on what Olga said earlier, you know, the concerns that application developers also in our lab have is, okay, I need to build something that runs on so many different systems. I'm not going to hunt for the last bit of performance. I'm not the maintainer of, you know, like PyTorch or so, where I actually have multiple code paths depending on which architecture I'm actually running on. So I'm not hunting for the last 20% of performance. I just need to make sure that if I compare platform A to platform B, I want to be able to use the same tool, actually have the same visualization side by side, and see, you know, where are the differences. And that is possible. And I believe this is, you know, where the various concerns, like Olga said, we can have both. And it has been a good collaboration in the past, and probably also in the future.
Look how positive you guys are. It's great. All right. So yeah, let me kick over to the next question here then, unless anyone else has anything to add on that one. All right, cool. So in the next question, I'm just profiling. We're asking, profiling and tracing can often generate enormous amounts of data to be analyzed for decision making. I mean, it's just a big data problem, essentially. As computers are growing in size, they're becoming like exascale, just as we've heard about in the keynote speech today. How best can we balance like these dual needs of collecting sufficient data for significant traces and not overwhelming users with too complex visualization or other methods of exploring the data? Yes, Lucas, please.
Yeah, I can start. So I think from the perspective of collecting the data, I think the trade-off would be to leverage the intrusion of the how much intrusion do you cause in the normal behavior of the application when you're collecting the data. So if your intrusion is sufficiently low, you can go forward and trace more data. Because if you don't trace sufficiently data, you won't have significant traces, or perhaps don't capture the behavior that you are trying to optimize. From the user perspective, I mean, about the complex visualization or exploration methods, I think that because the compute time in the supercomputer is very expensive. Sometimes you have to wait for 2 to 3 days to have some data. So if you trace fewer information to have a more simple visualization, that can cause you some delay in your performance analysis cycle. So my answer to that would be to trace as much as data as possible, causing the less intrusion, and then start with overviews. And then depending on what you observe in an overview, you can zoom in some part of the traces or the profile data to see where is the problem, where is the performance problem that you don't know where it is in the beginning. So I think that is a good answer, because it allows you with just one shot of one trace, you can do both. You can start overviewing and then zoom in specific data without waiting for more detailed traces or more detailed profiles of your application.
Olga, please.
So I think this is one of the chicken and egg problems in performance analysis, in that you know, you need to know what you're looking for to know what data you need to collect to find it. And so essentially we're talking about reducing the dimension of data somehow, right? So, you know, exascale, right? 1 million processes. Well, that's, you know, do you intend to look at the communication between the 1 million processes, or do you intend to look at the execution of a single process within that? And is it sufficient to look for outliers only, or are you interested in the overall performance? You know, what's the question that you're asking? And that kind of, you know, the tools need to be able to allow you to reduce the dimension of that data somehow. Lost my train of thought. So basically, right, so for some of this analysis, you're looking for also the other dimension is the runtime of your of the problem that you're dealing with, right? If you're trying to study a particular, you know, particular piece of your computation, do you really need to collect the data on, you know, a 2-day long run? Do you need to collect all of that? You know, so some of that, it really requires the flexibility on the tools part for the user to specify what they wanted to look at today. And I do like the suggestion that Lucas had, where, you know, if you were in fact able to collect a lot of it, then you have to be able to subset that somehow for the user to look at first, and then perhaps, since you've collected more data, then perhaps there is a way to ask multiple questions that look at the different dimension of that data.
I can just
go ahead,
jump in based on something that Olga said about the dimension reduction of the data. One of the problems that we have when we do that, it's like aggregating data, simplifying the data, doing averages and things like that. I think statistics plays importance and significant importance on this, because when we are doing some averages, we always have to take into account that we are playing with a very, let's say, non-deterministic computer, because it is too big. There is a lot of variability, and this type of variability has to be taken into account when you're playing with dimension reduction. So, for example, when you want to you have some function that you detected that it has a performance problem, and you want to do averages and things like that, and take a look into the variability of the execution time. You have to play to detect the outliers, and so it's very complex to just see, I mean, global metrics. I mean, you run the application, and at the end you say, oh, the problem is there, or the speed up is this. But perhaps during the execution, those metrics, they changed a lot. I mean, during the execution, in the beginning, it was okay. In the middle of the execution, something went wrong because of some hardware start doing something weird. And we want to see that type of detail. So that's why I, with my students here in the group, we always focus on the tracing part, because the tracing part, you have more rich information, because you can take a look into the historical evolution of those metrics, instead of doing global profiles that merge everything together, and then you just have a big picture. That's something that some people like to see, you know, just a number that say, oh, this application is good or not. But sometimes the reality is more complex than that. You have these fluctuations during the execution. So doing dimension reduction is very challenging on that matter, especially because of the size of and the scale of the supercomputers, the hardware that we have access to.
Yeah, here, let me, well, Mac's been waiting a little while. Let me get Max and then I'll kick it over to Guido.
Yeah, sure. I was just thinking while that was being said that while it would be nice if you could just collect everything and then reduce it later, and I think Olga was kind of hinting to this, you can't today, at least on a modern accelerated platform, right? Again, I will speak with some level of vendor bias, but we, you know, when I've looked at using our tool inside systems to collect traces of like a deep learning training session, if you collect that for more than a few minutes, you're going to have a multi-gigabyte file, and it only gets worse from there, right? And that's the nature of the fact that these are complex applications launching lots of little compute kernels. They have lots of memory operations potentially. And so even if you just restrict to tracing, right, forgetting the complications that come from like metric sampling, even just tracing can become unwieldy. You can't collect a 2-day-long run, at least on our tools, and I think many other platforms. You would have too much data. It would just become actually too large to collect. And so this is a bit of a speculative view, but I'm concerned, or I think that probably there's going to have to be some level of dynamic adaptivity in the tools in the future, so that as you run, you could figure out what do we need to be collecting, and then figure that out, or like set some sort of configuration file at the beginning of your run that says this is what I'm going to collect based on things that I'd learned in previous runs. And I don't know how you reconcile that with the great point that Lucas made, which is that what might be true at like time step 10 of your application could be very different from time step 1000, right? And if you don't know about that variability ahead of time, you might miss it. I don't know how to deal with that, honestly, but I do think that's a huge important problem that has to be dealt with.
All right, let me go over to Guido now.
So, one of the things that struck me was that, if you look at performance tools, like very generic, let's take the easiest one that we maybe all know, gprof, for example, is a tool that has been written for sequential serial application to kind of see, where is my hotspot? The problem is that most of these tools, and also the mindset of the tools, is the easy ones. Let's say use easy profilers. I just prepend something and I get textual output. Easy for the developer, easy. They don't pertain to parallel programs, because just because you're seeing that your MPI broadcast is the most often used function, that's not the root cause of your problem. The root cause is that one of your processes is behaving differently than the others, and you have a late arriver. So the standard profile will not point you to the actual root cause. The problem is, to find this root cause, you'll have to accept the fact that you'll have to, modify your application to provide more information. Like Lucas said, that's where tracing comes in. People hate tracing because it's complicated. Because essentially you modify your application to push out more data to an external tool or to a file to be analyzed later on. But essentially, from an application developer point of view, this is the most valuable information you can actually acquire, because it will, you can look at it yourself. And honestly, we've done this with trace viewers, and no application developer understands trace viewers. Even if we do 3-day-long trainings, you have to ship the computer scientist with the tool to actually explain what they're seeing there in those wonderful fancy colors. But actually what you can do is you can use other tools that then, run over this trace data and do those root cause analysis. John Mellor-Crumney's group has done wonderful work on this, and stuff like this has been percolating into other tools as well, where you basically, assign certain blame to certain function and generate new kinds of profiles out of those traces that basically tell you those are the functions that are basically, holding up your critical path of your application. And this is where you should look at. And Max, actually the research-based tools, they have some mechanisms for basically being turned on and off at certain application. But again, this requires the application developer to modify the application to kind of, say, okay, I want to, in your outer loop that does the time steps, I want to put something in that basically says, on iteration 1 and 2, turn it on, then turn it off, turn it on again at 50 for 2 iterations, and then turn it off, and so on. So this is, it's if you want to answer more questions, you have to be willing to invest into getting those answers. And as hard as it is, there is no easy way around this. I would also say that especially research-based tools, multiple gigabyte trace files don't scare research-based tools. I mean, we've done successful traces in multiple terabyte regimes where you then need a massively parallel program to actually do the data mining and behind your visualization, but it works. You can actually do that. The question is, if have you asked the right question at the beginning, which kind of circles back to what I said before, is if you only want to basically get a pinpoint of, is my code balanced? For example, you don't need to generate tons and tons of trace files. For that, actually, profiling is fine, because you generate profiles for every process, and then you look at it and see if they're all saying the same, then you're very likely balanced, very likely. I mean, there are always corner cases, but so actually, having some people like Max or Olga or so to actually that serve as like performance consultants is actually quite important in this. Think of it more like an interview process towards your application. You're going into an interview to kind of dig to what are the questions that are important, and that's extremely hard to automate. I mean, you can provide material for this that people can do this themselves, but as Max and Olga can probably say is, every interview you do is different. So at least after, the third question you've asked, you are on a different path than, what you've done in a previous session.
Thank you, Guido. Does anyone else have anything to add on that one? Perfect. I had a later question, but it feels kind of relevant to the discussion at hand. Is I was wondering how it seems to be that in general, machine learning, is touch on every aspect of computer science, generally speaking. And we see here, even in this workshop, we have performance analysis of machine learning applications. But I was wondering what your guys' thoughts were on where we might be able to utilize machine learning for performance analysis. I don't think it's something that's frequently done yet, but it's probably going to be more common in the future. If you guys have any thoughts on that. Especially, I was thinking, it seems like Max was talking about that dynamic performance collection might be a potential use case for something like machine learning.
Yeah, I was actually thinking about machine learning when I said that, and I didn't really want to get into it because I'm afraid of committing us to doing something that's a very hard problem. But it basically struck me that this is a machine learning problem, right? And that I think that probably that's what you'll see in the future. And I think internally, vendors like NVIDIA already do this to some extent, is to train machine learning tools on applications and the kinds of performance patterns that they have, and then use that information in helping you understand later other applications that might have similar behavior. And so I don't know, this may be a very speculative thing, but I do think that machine learning is a potential way to figure out as you go what kinds of things you should be looking at. Because while there is a lot of variation in the application space, there is this, there are some things that are similar across applications, right? That, that they take time steps or multiple iterations, and this concept that like there might be a steady secular drift in what's important in the application over time. That's a thing that's very subtle for a human to pick up, but could, ring out clear as day to, machine analysis tool. And so I do think that there's probably a pretty important role for machine learning in training on application traces or samples, and then figuring out what is unique or interesting about that application, and then using that to inform what kind of information you might want to follow up on collecting in the future. Again, I don't know that many people are doing this today or even capable of doing this today, but I would be shocked if we're not doing that in 5 or 10 years.
Yes, Olga, please.
We have kind of an important problem to solve before we can do that, though. I think Lucas mentioned this earlier. A lot of our performance data contains a lot of noise. And some of that, we understand, right? You're hitting a file system at the same time with another heavy application that's heavily utilizing it, or you're running by yourself, or network congestion, things like that. And so right now, even with our current performance tools, we don't even know how to essentially account for which of this data is noisy, right? And so one of the concerns that I have is that if you throw a machine learning algorithm at extremely noisy data, what are you going to learn?
I can comment a little bit about this because we have tried in the past to use machine learning to learn from the traces, let's say, and the conclusion was that most of the performance problems, they are for typical applications like iteration-based applications where you run several iterations, where you have compute, communicate, like phase-based applications, is that the types of performance problems, they are very common. They're always the same. So we have some tools such as Scalaska that is developed in Germany that allows you to automatically detect those bad performance problems. So you have, for example, late receiver or late sender that's participating in the collective operation and is being late for some reason. So the tools are already there that pinpoint those processes, so you can take a look into more details. I'm not really sure how machine learning algorithms could be used for classifying performance. Perhaps we could use clustering to detect groups of processes that behave differently collectively because they are part of a machine that is undergoing contention in the network, such as a very common problem. But I think it's very challenging. I'm not really sure how to apply, let's say, reinforcement learning, for example, in the tracing, because that depends a lot on typical problems that are, for example, noisy data, such as Olga just mentioned.
Thank you, Lucas. All right, cool. If there's no further thoughts on this one, I'll move over to the next question. Let me just check real quick, see if we got any more from the audience here. Nothing new. All right, we're good. Then for the next question, we've kind of touched on GPUs a little bit, but this question is more broad, and we're just asking, how are the growth of GPUs and cloud computing changing the landscape of tools and technologies we're currently using? We were thinking originally Guido and Max for this. So Guido, would you be willing to start us off on that?
Sure. I mean, let's start with something fully provocative here, and I'll have others throw at me. I would say that the standard cloud user that especially if it's from an HPC point of view, that fires up a Jupyter notebook in some cloud instance, couldn't care less about performance. They just want to get their stuff done, their solutions, and that probably extends to more cloud usage as well, unless the cloud usage becomes a little bit more HPC oriented. But we should also, as an HPC community, accept that a large part of the HPC users just want to get their results within a reasonable amount of time, and they are willing to apply for more compute time, if they just need it to run their problem on more nodes and so on. So they aren't really that interested in modifying their applications. Sometimes also because they don't have the resources for it. So it's that's probably one of the sad facts that we just have to live with. The other part of this, also with GPU or GPU computing, is it adds an additional layer of abstraction. You're one library away further from your actual code. In a lot of cases, you're encouraged and also right in using vendor or supplied libraries or some community libraries. The question also pertains a little bit towards AI. If I'm using a framework like PyTorch or something else, TensorFlow, how can I influence performance? The actual performance is abstracted away from so much from me. Even if I use a profiling tool, it will tell me that some TensorFlow internal function with an extremely cryptic name, if it maybe came from a C++ template, it's about this long and totally unreadable to me, is consuming 89% of my time. So, okay. I mean, the best I can do is then, fiddle a little bit with some parameters that I can do and see if things change, and if something gets better or not, and maybe I also get some hardware information that, I'm utilizing the GPU now better. But, let's be honest, I'm only interested in runtime and correctness of my result. Actually, that comes first. That's I want to get the right results in a reasonable amount of time. So the tools that we're talking about, in that space are probably for a more limited amount of, or a group of people than we are honest to admit. The ones that actually develop those libraries and those applications that are interested in squeezing out, more performance. For those, those tools are relevant, and making sure that, they have access to the right kind of information, which is, as I want to circle back to what I said before, is, those root causes. What have I done in my application that, is costing me performance? And like Max said before, those are extremely hard questions, especially if tools are mostly written from the point of view is let's extract, the platform information that we can and present this to the user. And yeah, I actually don't see much difference, whether this platform is a real HPC system or cloud-based HPC system, minus the fact that, as I said before, that, if you're using cloud systems through a browser, you probably don't care about performance.
Olga?
So yeah, as Guido was talking, I was thinking, actually, this is not a new problem. We have this problem on HPC systems. There's actually usually fairly disjoint groups of people that write code and people that run code to get scientific answers, right? And just to give you an example, one of the first problems we hit. Well, problems. One of the first instances of this we hit when we migrated our codes to GPUs was to notice that our users were heavily underutilizing the GPUs. And so what they were doing is the thing that they always do is they would strong scale to reduce the total runtime. And they may have reduced the total runtime by 5 minutes on a span of a day, but they used twice as many resources, and they only used, and if they actually used, half the resources, it would only be 5 minutes slower. But they didn't, they didn't understand the properties, the scalability and they just tried something and they went with it, right? And so it takes us a lot of time to go and figure out, okay, why are you underutilizing the machine so much? And then circle back to the users and go, okay, can you please next time don't quite strong scale it this much? This is roughly how much work you should have per node. Those kinds of that kind of guidance sometimes is necessary for running the code. And so and that's our internal codes, right? Libraries have it even harder, right? They don't know who's using their code. How they're going to use it, that's tough.
Max, please.
I agree mostly with the set of facts that Guido mentioned about cloud computing, right? I want to put a different spin on it. Cloud computing is a very competitive landscape because in some sense, the major cloud vendors are all providing more or less the same service and need to differentiate themselves in some way. And when your goal is to provide a platform or some piece of software as a service, that means that you need to be just very slightly better than your competitor, right? Because like if you're running the same application, it's hard to be orders of magnitude better, right? And so one consequence of that is that because the landscape is so competitive and the relative differences in performance are relatively small, I think that the cloud distributors themselves, folks like Azure and AWS, are very focused on maximizing performance for their customers, right? Guido said that the customers don't care about performance, but I think what he really meant to say is they don't care about performance analysis, right? They're not going to go in and optimize that application, but that doesn't mean that they don't want, ANSYS or whatever tool that they're using to be as fast as possible. They would like it to be as fast as possible. And if the competitor cloud service can do it 10% faster, they're going to go to that other, at the same cost, they're going to go to that other cloud vendor. And so I do agree that there's been a kind of centralization where it's the experts who do know, who can understand, you know, a PyTorch trace output and understand what do I even do with this, which is a very select group of people. It has been moving in that direction, but one, you know, counterpoint to that is that even those experts are humans too, right? And most of those experts themselves would struggle with this. You know, even our experts, if you give them, you know, a trace of a 10-minute PyTorch training session, still have to think pretty hard about what's going on here and how would I optimize this. It still requires a lot of work. And so I would say that the trend that I observe is that the tools are, at least our tools, and I think other tools too, are trying to move in the direction of, given that cloud computing workloads tend to produce very complex traces with lots of information going on, and you have to dig deep to understand how to optimize that just a little bit further. The key is really to sift out as much as possible to make that easy to do, or at least easier to do, to figure out where do I even look in this gigantic trace output to optimize this. Because, like I said, even the experts themselves aren't really experts, right? They themselves have trouble understanding what's going on and need tool assistance to figure out where to look to optimize this.
Yes, Lucas, please.
Yeah, I just want to jump in about this cloud computing and HPC because usually when we do the performance analysis in a supercomputer, we try to simplify the analysis by controlling stuff. So we control the frequency of the processor, we observe the network contention, if it's going on or not. And if I go to the cloud computing environment, usually this type of information is not available. So because of the vendor rules, because it's because of the virtualization, and I think it is very important to have this type of information when you are doing the performance analysis, even if it's hard to obtain, because otherwise your performance analysis will be very specific to a session in your cloud allocation. Because if you run the application today, you had some virtualization configuration going on the real system there. And if you do the same performance analysis tomorrow, the performance could be another one, completely different. So how do you make things predictable? To do that, you have to measure things. And I think the cloud vendors should provide more information for the performance analysis specialists, because in that case, you can take a look to the performance of your application, but also knowing what's going on there, and you can correlate things better. And that is very hard. We have tried in the past here in our research group, and it's very hard to obtain real measurements of what's going on about the contention of the network, or what types of virtual machines that are running there, and things like that. So it's very challenging, and I think today's tools, they just don't have this type of information to provide to the performance analyst.
Yes, Max, please.
I'll just briefly comment on that point that, you know, Lucas is absolutely right, that's something that we have had to grapple with at NVIDIA, is that so many of the consumers of our tools now are running on virtualized or containerized environments. And that does pose challenges for the kinds of things that we collect. And, you know, there's complex concerns, but there's also more mundane concerns, like, you know, we didn't have the right perf paranoid level and couldn't collect CPU samples. And then how do we present that to the user, right? You know, how do we, what kind of, you know, how do they ask for that? And we see that in HPC environments, containerized workloads are increasing in relevance, both within deep learning, but also, I think, starting to become more relevant for traditional HPC applications as well. And system administrators are, I think, grappling with this fact that, like, containers pose challenges for security and their security posture, and they're not used to relaxing these kinds of security rules for collecting this kind of performance information. And I agree that that's one of the, I think, how cloud computing is touching HPC is that it's forcing traditional HPC system administrators to confront this idea of moving towards more virtualized containerized workloads. And then they have to figure out, how are we going to let our users run in a way that they can actually get useful performance information out of the system. That certainly the hardware vendors need to support them on that. But there's some level of, we just need to understand a new policy and a new, you know, design new systems to support this. I think we're in the middle of that transition right now.
Yes, please, Guido.
So to, after my blunt comment at the beginning, let's maybe also give some silver lining here. I mean, this abstraction through cloud or containers also offers a great chance for hosters or HPC systems providers, because we all know how troublesome and difficult it is to, if you want to implement some always on profiling for your jobs, you have to get all users to agree to this and so on, and then you have to tie this into your batch system in some form so that some reports get written, and then but this gives you a very valuable pile of data that you can do wonderful analysis with. Being able, just to be a cloud hoster, or to have, if your people run containers in your system, you can actually make this always on performance analysis part of your basically base image, your host platform that is always running. So you get some maybe not the level of detail on the actual application level, but you can basically see certain patterns in, okay, there's this user that is always running this container, and I'm seeing those, performance characteristics on my host system all the time, or same also for cloud platforms. So this, might also give actually the providers some benefit of basically having performance analysis always on for their benefit to kind of see if the system is behaving as expected, and the actual user doesn't even know that there's some performance analysis running in the background. So that is also an opportunity, also for performance tools, by the way, and maybe then also for machine learning, because that data you generate there might be generic enough to actually be thrown into those data monsters.
So I see Olga excited about this one.
Yeah, so I actually wanted to ask, why do you think the user needs to know that you're collecting?
I'm from Germany.
data?
We have some data privacy concerns about everything. Sometimes rightfully so. So, looking back at our history, it's sometimes good to know what's happening with your data, and users are usually concerned.
Right. So I
know
think
that. Yeah. Go ahead.
I think we need to be a little bit more nuanced about what data is okay to collect and what data may not be okay. So for example, we have worked very hard with NVIDIA, for example, on our Sierra system, specifically because we wanted to collect information about GPU utilization type of thing. And well, there is no privacy expectations on our machines. But the main concern we really worked around is for it to be always on, it had to be cheap, right? It needed to not interfere with the performance of the codes themselves. And so the big deal that we worked through with the help of NVIDIA was, the interface to get that data and to get that data efficiently. And it is, it has been very useful, and that, and it's not even cloud, right? It's just traditional HPC at this point, and we're still grappling with a way of, how do you get that data, and how do you get it in a way that you can always leave the collection on, and you can make some sense of it later.
Yeah, and honestly, I envy you for just being able to do that. I'd love to have
specifically,
such data
right?
For
This was the you can make a distinction of what you're collecting, right? GPU utilization, you're using half of your GPU or all of your GPU or none of your GPU, right? What privacy do people need to have about that, right? It's not, right? It doesn't tell you anything of what they're computing. It just tells you how they're utilizing the machine. It's hardware. It's a hardware question, so hopefully it's okay to ask.
Yes, and honestly, the concerns we had were just job names and executable names. That where people all of a sudden were complaining here. So I don't want to know I don't want the data center to know that I'm using application XYZ all the time. Yeah. And
okay.
So, but we're drifting off into some weird things here. But yeah, it's at the same time, you know, one of the other things is also that if you're collecting that information, you need to have personnel that actually does something with that information. And especially for my data center, we are just a tier 3. Our local data center is just a tier 3 data center. We have like 2 half FTEs that actually run all HPC resources. They don't even have the time to you know, do anything with that information. So that's why we're not doing it. Although I'd love to have this and just give it to our AI people to play with it.
All right, thank you guys. It looks like we got another question in from the crowd here from Randy Rano. And he says, comment about, quote, even experts have a difficult time understanding what can, so yeah, quote, even experts have a difficult time understanding. I can't remember that one of you guys. But what can the HPC community proactively accomplish in terms of transparency? Enable a broad range of stakeholders to have some insight on operation, as trust is perhaps critically important to the community to continue in realizing opportunities. I guess the main question is, what can the HPC community do proactively to establish transparency?
I'll take a shot at this. When you're looking at understanding the output of a performance analysis tool, the challenge is that the user is often the most, like the end user, who is the domain scientist, in my view, is in some sense one of the more important consumers of this, because they're the people who have the least knowledge of the platform, of the architecture, and therefore you can't lie to them. Like, you can't lie in the sense that if you write a tool that is incomprehensible to quote unquote the layperson, you'll know, because they just won't be able to do anything useful with your tool. And so probably a shift towards focusing on, as much as possible, making the output of our tools accessible to, at least in some way, to people who don't have much expertise in something, to get output from it. That's probably one way to do it. And so what I mean is, most of the tools that we write in the performance analysis community are designed for people who understand their application very well, and who can then marry that with their knowledge of the application with what they're learning about the tool from the platform to make some optimization. But if we focused on making it as easy as possible to get very high level rolled up metrics about what's going on, so that even the non-expert could understand what's going on, at least at a high level, about the application, that might help. And so that could be things like collecting high level utilization metrics, like we were just discussing, during your run, so that even the manager of the person writing the application, who doesn't really know any of the details, could look at the tool and understand what's going on. If you force yourself to be able to do that, that probably forces you, I think, to not write the tool just for the ninja, but so that anybody looking at the application trace or whatever could get at least some level of information from the output, with the amount that you can glean from it based on your level of familiarity with the application. But it shouldn't be zero if you are just generally an HPC person, but not a user of that application. You should be able to get something out of this, at least be able to say at a high level, how well did this tool, this application, use this hardware during this job?
Yeah, Guido.
I mean, since the question also built me the bridge to lay some burden on the application developer here. A thought that just came to my mind as Max was answering is, one thing we could think of is also having the programmer provide them, or have a method to provide more context to the tool of what's going on. So like your previous question about diverging APIs for tool developers, one could also rephrase this and say, it would be great if there were a mechanism where special comments or it's directives or something in the code or function calls, standardized function calls that basically give the tool, performance tool, some context, like this is an initialization phase. I'm going to do some IO, just some human readable thing that the tool can then, output back to the user. Hey, I recognize in your code you specified 5 code phases, or this is you said those are now my iterations of the code. I expect them to be similar or something. That the tool can capture and annotate with or provide you the structure of the report in the same way as the structure you specified in your application. That's not there yet. Especially, if we actually want to do this in a standardized form where the Insight tool from NVIDIA understands the same way as ScoreP, for example, does, or, any other performance, or Tau, or you name it, so that they can all at least accept this, and then what the tool does with it is on a totally different story. But, having those richer comments, that are not just comments that are ignored by the compiler, but where actually something can be done with it that provides context, would be a good direction, I would see, for closing this gap.
Yes, Olga.
So Guido, that's very interesting, because that is actually the very next thing we had to do once we got the GPU utilization data about our machines. Just knowing this user for this run had a 17% utilization and this other one had 90, and you look at them and you're like, they ran the same application. What is going on, right? That was the very next step of what we had to do to sort of work out that puzzle. It turned out the first user was dropping restarts every minute, right? And so the very first performance hit that person took was writing out restarts too often, because they were writing them at the same frequency as they would on a CPU machine, except our code was running 20 times faster, right? And so that was very key for us to kind of start looking at this. And then, we had users that were, for example, working on what we would call the setup of the problem. So they would start up the problem, they would run one cycle, they would look at what they're simulating, and they would go, oh, I want to resolve more over here. And they would start again. And they were not in fact running, they were just starting up, right? Starting up. And of course, their GPU utilization was pretty low for that, right? But that is a very valid use of the code, right? That's what they're doing in order to simulate something. So it's not like you can say, oh, you're not utilizing the GPU enough, you shouldn't be running. Right. So that is very that is, I think the tools need more information of the intent, right? And I think that's a big disconnect that we still have, is, what is the person that's running the code, what are they trying to do, and what are the different pieces that they're executing, and with what frequency and for what reason. And yeah, right now there's not a standard way to tell that to the tool. So this all sort of happens. We're able to collect that information now in one way, and the actual utilization in another way, and then there is a human in the loop that puts the pieces together. But a single tool cannot do all of that.
I saw Lucas, you raised your hand. Yeah.
Yeah, I just want to comment about the HPC transparency and the performance metrics, such as the one that Olga just mentioned about the GPU utilization. I think it is very important from the user perspective to know exactly how each performance metric is calculated. I mean, have like the source code of the performance metrics in a way that if the person has an issue trusting those performance data, the person can actually knows how it has been computed. And this is very frequent with my students, because sometimes they come up with some plots showing performance metrics, and but how do you compute exactly this point? So I think the HPC transparency and the tool, how the tools compute those data is very important. And I think it's a little bit part of this open source discussion that we have previously.
Thank you, Lucas. All right. We've got about 5 minutes left. Let's see. It goes over a little bit. I'm sure it's okay, but let me see. I'll just kind of close this out with one question about, as I'm sure you guys all know, the co-chairs here are all students. So we have the obligatory student question for you, which, and I'm sure that many of you have worked with students. I know some of you directly and some with interns over the summer and the like. I'm curious, what changes do you feel should be made to HPC education to prepare students for the changes we're seeing in HPC technologies? Let's start with Guido over there.
So I would actually, you know, for my alma mater, which was TU Dresden, the biggest change computer science faculties, in my opinion, have to make is accept that parallel programming will be here to stay. And, you know, not teaching parallel programming on an undergrad level is like the worst thing you can do. It's not even mandatory on the master level at TU Dresden. So basically, it's optional to learn about parallel architectures and parallel programming. And those will be the people that will then use the cloud or whatever resources that we provide later on and that build the future systems. The second thing that I would also advocate is that we need to make sure that all HPC education is as interdisciplinary as possible. So you need to push them into those physics and biology and whatever faculties where they actually get exposed to the users, or actually the other way around. You know, HPC education can also be for physicists, biologists, and so on. So you need to make sure that you take them out of their comfort zone, you know, the faculty that they've always been in, because HPC is highly interdisciplinary work. Like what Olga said, you know, like they're forcing basically people from different domains in one room. The greatest, you know, people that I've known in HPC are the ones that actually could do this within one person. Basically, physicists that were so interested in HPC that they, in theory, could have gotten a PhD in computer science as well. Or the other way around, computer scientists that cared enough about physics or, you know, the biology problems that they understood them, let's say, well enough that they could communicate on the level with the, you know, with the domain science PhDs on solving those problems. And, you know, this is something that is, in my opinion, extremely neglected, because it feels like every faculty is trying to hold on to students too much and not allowing this interdisciplinary nature that HPC traditionally has between domain science and actual computer science. And actually, if you're honest, also, you know, there's numerics and mathematics and, you know, a lot of theory also behind this as well.
I saw Lucas ready to unmute there. Yeah.
Yeah, I just want to compliment. I fully agree with the interdisciplinary that Guido just mentioned, but I want to give you an example of surprising gaps that might come up with working with the students. So the computer science course in general, they have a lot of system level, such as compilers, operating systems, distributed systems. All of those work as a background for HPC. So at a given point, the student will move on to the HPC technologies such as MPI, OpenMP, OpenACC, and OpenCL, and things like that. But the surprising gap that I have found with my students, it's very frequent, is that when we play with these different performance tools and application code, sometimes the students have a very big problem compiling the things, you know, configuring, accessing the system, because the compilation doesn't work, because the compiler is not right, or because there is the version is different. You know, these very basic things that are not taught in any course. They are part of the, I don't know how I think I have learned this by working with scientific initiation and having an advisor very early during my undergraduation. But I think there is no course precisely working with bash scripts, debugging things very, and I think this is, I don't know how to tackle that as a professor, perhaps I should propose a course on that, but that is very specific because it's problem oriented. So it depends on the application. So this, let's say, sixth sense about how, you see a compilation problem, you say, oh no, but this is this. Have this sixth sense about this. It's very hard actually to give the student somehow. I think it's only the experience, the time provides you that, and I don't know how to fix that. But that's a gap I have found with my students in the last, let's say, 8 years already. So it's very common.
Wow. Yes, Olga, please.
That is very definitely a big gap, and I think we sort of approach it with two opposing solutions. One is, make it so they don't have to do it, right? That, I mean, I'm pretty sure that's somebody came up with containers and things like that, right? So you give them pre-built things. And if you really intend for them to make some progress in a span of 2 months project, you essentially have to avoid that, which, in a sense is doing them a disservice because, as Lucas was saying, I think the only way, at least that we know of, that you can learn this is by beating your head against the walls. Yeah, that's certainly a big gap, and that's because it's it's not a single skill. It's like a whole lot of things wrapped in there. And what is the problem? How do you diagnose this? If you can at least identify what the problem is, you can then attempt to start Googling this for the solution. But it's the first step of what just happened. What went wrong here? That is very hard to figure out and make that leap to asking a coherent question that might lead you to an answer.
Max, have you worked with any students, interns, or anything like that?
Yeah, I wasn't going to say anything because my point largely just echoes what Olga and Lucas just said. But yeah, I mean, any student coming up today is going to be in a position where what they're learning now is going to be very different from how HPC looks in 10 years, right? There's no student coming up today who will not see technology significantly shift on the span of their career. And so to me, I agree that, and because most of these people are coming from a domain science background, not computer science degrees, I think, to me, I think the most important skill is in fact problem solving, right? When the thing doesn't compile or when the code crashes, how do you think about that, right? How do you understand how to think about that problem and not just go and ask your PI for help, right? And you probably will the first couple of times, right? Every student that I've ever seen, including myself when I was a student, we come running for help to our advisor the first time or the first 100 times, right? But eventually you have to build that skill of how to think about the problem solving yourself. And while I agree with the point that some of this is application specific, there's a lot of this which is very generic, right? How to use Linux systems, how to use debuggers, right? Even if like learning GDB is a specific skill, you might argue, the general concept of how to debug an application and like what to look for and how to think about the state of the application at the time that it crashed, that's a very universal skill, and people should get more practice with it. And even if it's true that things like containers are making some aspects of this universal, I just think the bugs that they will hit will just change, but the general nature of finding and fixing bugs isn't that, I think, different, even if the technologies themselves change.
All right. Well, I guess, unless Lucas, do you have one more thing you want to add?
Yeah, just a small thing about the preparation for the future. I mean, the things are, computer science in general is it evolves very rapidly. We always say that. And HPC is not different from that. But I think you have to make a mind positioning, and you have to be open for the changes. And sometimes the students, they are taught during their undergraduation and graduation in some technologies such as MPI, OpenMP, but that might fully change in the future. And in being open to learn new things, I think that is the most good advice I could give to any student working in HPC, because things are going to change every day. You know, NVIDIA came up with the GPUs, and then suddenly you had to learn CUDA, and in the future something else will come up. So we have to be, and you don't know now what it's going to be. So you have to be open to these new technologies coming in, and new libraries, and new interfaces, and new APIs. Because the fundamentals, I think they are okay. You know, as I said before, the undergraduation, the system level disciplines, they prepare the students for the basic concepts. But the technologies, I think you have to be open, always be open to learn new things. It was just this quick comment. Thank you.
Yeah, thank you, Lucas. All right, and yeah, that should pretty much be the end of the panel. I just want to thank my 4 panelists again significantly for volunteering their both rare and valuable time to us to edify us about the future of performance analysis. And with the end of the panel, that also means that it is the end of the workshop. And so in addition to my panelists, I would also like to thank the program committee, everyone who submitted, everyone who attended, in addition to my wonderful co-chairs who helped me out throughout this whole process. Anna herself contributed many of these questions for the panel here. And really, without these two, this would not have come together as strongly as it did. So thank you very much, Radita and Anna. And I believe that's it. Look, there's her face. There's at least Anna's face. Thank you guys so much for attending, and look for this recording. We will post it on the Permavost website, probably hosted through YouTube later on, and also keep an eye out for the was it the proceedings, which Anna actually linked earlier, and maybe she could drop another link in, or Radita, Anna or Radita, I can't remember. All right, thank you guys so much. You have a great day. Enjoy your getting back to work today.